Ora si registrerà la conferenza.
Sorry for that. It was just we are registering the tool.
Okay,
Sorry.
all good. So what you see here is the summer temperatures for Switzerland between April and September. So each vertical line represents one summer, and this is now between 1864 and 1992. And you can see essentially Gaussian fit to that. And if you now go to the more modern period, starting in 1993 here, you can see this shift, and the shift is about 2 degrees, which is about how much Switzerland has warmed under climate change. You can see these 3 extreme summers that we had, 2022, 2003, and 2018. You can also see that the coldest year of the modern period, 1996, is still warmer than the average of the former period. So essentially, we're really, we're really warming a lot, so we have to worry about these heat waves. And Emanuele did a nice paper that he already presented to you in this workshop, showing that the most intense heat waves have really become much more frequent and much more intense during different periods or over with climate change. So this is something that we should be really worried about. So I'm going to focus here on the most extreme one that we had in Switzerland, because that one was, of course, not just an issue for Switzerland, but it was an issue for essentially the entire Northern Hemisphere. We see this here where Europe was extremely hot during the summer. There was wildfires in Sweden, for example, because there was an accompanying drought. North America was extremely above average, and then we also had this heat wave up here in Siberia. So this is now the 3-month average. So essentially the entire summer was really, really hot. And these conditions can be brought about, of course, by atmospheric conditions. These can be interact with underlying wind and ocean winds, as you've already seen in this workshop. So I'd like to pick out 2 specific examples, a warm and a cold episode during the summer 2018 heat waves. So one was at the end of June, early July, where essentially the jet stream dipped south, and we had a kind of cold period for Europe, at least for eastern part of Europe, but also here you see Italy is included. And then we had another period, the end of July, early August, where the jet stream essentially went all the way north, and we had this very hot period. So this is one of the periods we're going to focus on. So what we try to understand is how predictable these particular periods are, because essentially, if you want to, if you have this issue with climate change that, things are going to become, heat waves are becoming more intense, more frequent, then you might want to know when exactly they occur. So generally, we can't really predict much more than a week ahead, but the nice thing is for heat waves, we might be able to do better. So this is, again, the time axis for summer 2018, and this is the forecast lead time. So essentially, a temperature anomaly is well predicted if the same color essentially extends as far as possible up in the vertical. So you can see here for this hot period here, you see that for about 3 weeks almost, we have a pretty good prediction of those temperatures. While for the cold spell, there was at least a little bit of cold during that week, there was a much poorer prediction, essentially out to about a week or 10 days. So we wanted to know, is this a general thing that hot spells are much more predictable than cold spells in summer, and not just during this 2018 event. So we looked at how predictable summer heat waves are, and we for that we used the extreme dependence index. I'm going to show you how this what this looks like. I'm going to here focus on Western Europe. So we checked hot extremes and compared them to average temperatures, and in this plot here, where we're plotting essentially the extreme dependence index for average events versus the one for hot extremes, we can see that everything that's to the left of the diagonal means that hot extremes are better predicted than average temperatures. Everything that's to the right means hot extremes are more difficult to predict than average temperatures. And here are the different colors, they represent the different lead times. You can essentially see that for all lead times, essentially from 1 day to more than a month, everything here is to the left of the diagonal, meaning hot extremes are always essentially better predicted than average temperatures. So we wanted to understand, okay, hot extremes seem to be better predicted than average temperatures. What about different extremes of heat waves? And Maria has done some work on this, where she looked at are very intense heat waves better predicted than just regular high intensity heat waves. So she looked at different thresholds. One was above the 87th percentile, and one was between the 75th and 87th percentile, which is the high intensity heat wave. So essentially, for Western Europe and Eastern, we did this for 6 different, six different European locations. And in general, you can see that if you look at the ensemble members with the correct prediction of the onset of the heat wave, then you can see that in general, the extremely high heat waves have a better predictability than just the high intensity ones in general. If you now switch to, because we also want to not just the onset, we also want to know how intense these heat waves are going to be. For the intensity, it's a bit less clear. So we have a signal for only some of the regions where we have the extreme high intensity events that are better predicted than the high intensity events. So that's for the Black Sea, Scandinavia, and Eastern Europe. However, for the other regions, there's no such clear signal. So here you see the example for Eastern Europe, where we have a slightly better prediction of the very intense heat waves. So let's go back to that really extreme heat wave, or extreme period of the heat wave during 2018, and the one at the end of July. And this is the heat wave when you look at it in era 5. So what you see essentially is that there was anomalies about 5 degrees above normal, so that would count among the very intense heat waves. And if you look at how well it was predicted about 3 weeks before, then you can see that essentially the area of the heat wave was very, or the location of the heat waves was very well predicted. However, essentially the amplitude of the heat wave was not quite captured in the model. Now this is the model, the European model. So if you look at what the distribution of the ensemble members tells us about capturing this heat wave, what we want is essentially this distribution. So this is temperature anomaly. So we want this distribution essentially to center at the observed value. You can see that already 4 weeks ahead of time, before this heat wave occurred, there was essentially a preference for above normal temperatures, and already about 30% of the ensemble members were above the 90th percentile. If you go to 3 weeks lead time, this is the one where I showed you the figures just before, you can see that this becomes much more clear. So essentially the entire distribution shifts up towards the observed value, and essentially 2 weeks ahead of time, we had essentially a perfect prediction of that heat wave. So 2 weeks before the event, we already knew this was clearly going to happen. More than 90% of the ensemble members predict temperatures above the 90th percentile. So these are some very intense heat waves, and we're trying to better predict them. We're also trying to better understand why they are happening in the first place. The interesting thing for this one was at the end of July, there was actually, at the same time as that extreme heat wave in Northern Europe, there was also a heat wave here, essentially extending all the way from Alaska down to California. I had record-breaking temperatures again, 51 degrees in Death Valley, breaking temperature records from like almost 100 years ago. And so the question we ask is like, what are the main drivers here that we can look at? So we looked at essentially, could there be, could this essentially almost circumglobal wave here be an explanation? And we looked at 2 possible mechanisms. So one was local Rossby wave packets. They might be occurring in phase at at some longitudes. So essentially, they might be occurring here and here at the same time, just by chance, essentially. And of course, and then there's the other hypothesis of essentially planetary scale stationary waves with synoptic scale wave resonance at the same time. So we tried to understand what was going on, and we just looked at that particular event again, and looked at when Rossby wave packets occurred for that particular heat wave. So here again, you see the temperatures that were above the 95th percentile during that time. So again, you can see here, Northern Europe was strongly affected, and then also large parts of North America here, especially at the coasts. Now, we can compare this to the meridional wind anomalies. So essentially, there was strong anomalies essentially deflecting heat towards these regions. So there's essentially poleward. So red means poleward anomalies of the wind. You can see the same thing here. so essentially polar transport of warm temperatures. And you can also see this is now the Rossby wave packet envelope that Maria calculated, and showing essentially that that there's an envelope going all the way from North America all the way to Northern Europe. So the heat waves over Northern Europe, in this particular case in 2018, were essentially related to the same Rossby wave packet in this case. And there was a separate one up here and over here in part of Alaska. So the question then was, is this case an exception, or is this a rule over these particular regions? Again, was this just a 2018 thing, or was this really a general thing? So what Maria did is then doing a cadence clustering applied to all the heat wave days. The input here that she used was extreme temperature daily index, essentially a 1 or 0, depending on the temperature anomalies. And this for both the northern and southern hemisphere, is showing the northern hemisphere results only here. We ended up with 42 clusters, and we selected them, or we essentially distributed them into concurrent clusters and non-concurrent heat wave clusters. So all the ones that had heat waves in several regions that were strong enough and essentially large enough were selected, or were essentially defined as concurrent clusters. All the other ones were defined as non-concurrent clusters. So here's the definition that used for the concurrent cluster. So there has to be at least 2 regions with a certain number of grid points that have a certain area. Then as a diagnostic for the global wave amplitude, this was essentially just a Fourier transform of the marginal wind anomalies for some of the wave numbers 4 to 15. And for the local wave amplitude, this was the Rossby wave packet envelope following the paper by Freckles. So I'm just going to show essentially the most important clusters, and the one that we're interested in for example, the 2018 event. So if we have a concurrent European and North American heat wave, that is indeed generally related to a single Rossby wave envelope, Rossby wave packet envelope. So you can see here, this is the envelope composite that you see happening at the same time. The marginal wind composites, which essentially also are crossing the North Atlantic here, and the related temperature anomalies. So for this cluster, essentially, it's just that the Rossby wave packet envelope encompasses essentially parts of North America and parts of Europe at the same time. Now, I'm going to show also a different cluster which has 4 concurrent heat waves, but these are then driven by separate Rossby wave packets. So these are different heat wave regions, including the North Pacific. So this would be the one here, the North Atlantic here, then North America and Asia. So this part here over here in Asia. And if again you look at the envelope composites, you can see that essentially these are all related to different envelopes that which just happen to be there at the same time. So essentially, there's not a stationary wave train at that time due to these, but essentially it's just different Rossby wave packets that happen to be there at the same time. So in this case, there's no need for the stationary wave trains for the occurrence of concurrent heat wave, but essentially they just have the Rossby wave packets just happen to be there at the same time. So then Maria did this analysis of just checking what are the heat wave probabilities during essentially when you pick all the regions that have a high Rossby wave packet envelope during a particular day. And if you look at this for all the heat waves, then and again here the strongest heat waves would then be the green and blue areas. So the highest heat wave probabilities you then see over North America, so this part over Greenland and then over Tibet. For concurrent heat waves, this looks not too different, but again, Alaska and Greenland and Northeast Asia. And for the non-concurrent heat waves, it looks a little bit different. You end up with essentially Eastern North America, and again, Greenland and Northwest Asia in this case. So these are the areas that then have the highest, well, that have heat waves during when they have the highest Rossby wave packet envelopes. In this case, this was calculated as more than 1.5 standard deviations of this envelope. Now, interestingly, some of these high probability regions correspond to essentially Rossby packet onset regions. Those are the ones that are documented in this paper by Gluck and Witt from 2014. So these include a range of regions, one on the American East Coast, around here, then one on the East Pacific, and one off the coast of Japan. Okay, so this is what we're trying to distinguish between what do things happen at the same time just because there's a certain global wave, or does it happen because there's Rossby packet envelope? We also did essentially a similar analysis with a model and try to understand when do you get a certain global wave and when do you get a different kind of pattern just due to local anomalies. I'm going to go back to the model that Emanuela already introduced on Tuesday. So this is a hierarchy of different model components with the so-called icon model, where we go all the way from a dynamical core to essentially a complex physics model, and essentially step by step include all the ingredients that we think might be necessary for heat waves, and check at each step, how do things change in terms of heat waves? Can you now better represent where they occur, how long they are, how intense they are, and so on. So in this experiment, and Emanuela introduced this a little bit on Tuesday already, we use now, I'm just going to show the simplest part of the hierarchy, which is essentially just the dynamical core of the model with a thermal relaxation. So this is the equilibrium temperature that we're using. So essentially, it's this one here. So all the temperatures are relaxed towards that temperature equilibrium in the temperature tendency equation in the model, and add a relaxation, a certain relaxation time scale back to essentially this profile. So this time scale goes essentially from just a couple of days all the way to 40 days, essentially here in the free troposphere. So we checked that what happens at during a heat wave in the atmosphere when we have no topography. So essentially, this is a very simple model, pure dynamics, no moisture, no radiation, and we have just a flat surface. So we centered in on the location of the heat wave, and so this is essentially relative longitude and relative time with respect to a heat wave happening in this location. And what you see here, this is now 500 hectopascal Chip-Lange height anomalies. These essentially are just propagating past the point at the center here, where we have essentially this Rossby wave train, which is essentially going past this heat wave at the center, and essentially amplifying that location, and then they keep propagating. There's nothing happening essentially at the same time here, so there's nothing circumglobal happening at that time of the heat wave in this location. So for example, if this was Europe, then we wouldn't probably have another heat wave happening here in North America, but we essentially just have that one heat wave. So what we did then is we added topography, again, very idealized, a Gaussian mountain of 8 kilometers at 45 degrees north, and this is important, as I'll say in a second. So now we still have this kind of wave train down here that's propagating past the heat wave area here again in the center. But at the same time, we have this essentially certain global pattern that happens. So essentially the topography is essentially making the wave more stationary and essentially causing things to be more stationary around the globe. And we have these different patterns which could lead to heat waves that occur at the same time. So this idealized configuration is able to already create conditions of a certain global wave train with concurrent heat waves without any kind of feedbacks from the surface. So what's happening here essentially, if we don't have topography, we have phase speeds that are distributed in the entire range. And as we increase the height of the topography, I showed the 8 kilometer one here. We did intermediate steps as well. Then we're essentially slowing the phase speed of the waves, and we're centering them on essentially a very small phase speed so that the waves are much more stationary than before. Now, importantly, this behavior is only observed if the topography is located at or close to the location of the jet. because if we essentially shift the topography out of the jet region, then the heat waves or the waves are not reacting in the same way, or essentially much less. Emanuela showed you the experiments with the surface roughness, which essentially give us a very similar message in this case. This could have implications, of course, for climate change. Essentially, if the jet is shifting under climate change, you will encounter different regions of different topography, encounter regions of different surface roughness. So this will then, of course, change where exactly heat waves will occur, and potentially then also where areas of potential concurrent heat waves might be occurring. So in summary, for this, we have summer hot spells. They're much more predictable than cold spells or normal temperature, and the more intense heat waves are more predictable than the weaker heat waves in general. As an example, for 2018, we saw that there were concurrent heat waves, and they were very predictable. Actually, the heat wave in North America was also very highly predictable at the same time. So we were curious if that was related to different, essentially a certain global wave train. In this case, in 2018, it looks like these heat waves in North America and Europe were essentially related to the same Rossby wave packet envelope with no certain global wave pattern showing at that time. We then used hierarchical modeling to get further insights into the drivers of concurrent heat waves and the potential changes with climate change, and found that essentially you can yield, or you can get certain global patterns just by essentially slowing the waves by topography. So depending on where the jet is, this could lead to changes in where exactly the heat waves occur. So Wolfgang is also going to have a talk today and talk a bit more about these topics. So stick around for that one. Thank you very much.
Thank you, Daniela, for this nice presentation. And any questions? Yeah, Tiffany, please.
Hi, Daniela. That was a really great talk, kind of summarizing different components. I wonder if I could ask a question about the connection between the two parts. My takeaway from the first part is that it's no circumglobal wave, and so then it begs the question of where the wave packet comes from, and obviously a candidate would be the tropics. And the second part, which is all circumglobal. So do you think topography has any role to play in the real world in summer for what we're seeing? And if it's not topography, then what is the source of the Rossby wave packets that you clearly show in that top figure?
Yeah, thanks, Tiffany. Good question, because it's difficult to essentially connect those two, because in the idealized model, essentially we're seeing that clearly we can produce certain global wave patterns, but the question is, in the real world, can they also just happen to be there by chance because we have Rossby wave packets that essentially just happen to be there at the same time? So to be honest, at current, we can't completely reconcile the idealized model results with the real world. We're currently doing experiments with adding more complex parts of the model to see what if that changes anything. I think in general it can happen that you essentially it looks like a certain global wave pattern in the the long-term average, but essentially it's just different source region of Rossby wave packets that happen to be there at the same time and essentially cause heat waves in different locations. So that's what's happening in the real world. At the same time, in the model, we can reproduce these certain global waves. So we're currently trying to essentially reconcile these two parts.
Adrian first, and then Federico. Okay, Federico.
Federico, yeah.
Thanks, Daniela, for this really interesting talks. And just about this latest thing about the sensitivity experiment, removing the orography. Have you tried also to look at the southern hemisphere to see if there are like similarities to compared to what you see in a kind of idealized experiment? So I expect I expect to have Rossby wave packets less, so less concurrent heat waves event in the southern hemisphere. Is that true?
Yeah, so I mean, for the it actually doesn't really matter which hemisphere you're in, because we're just, I mean, essentially we have a flat surface with one mountain, so it's I mean, neither similar to the northern or the southern hemisphere. But I think the interesting part here is that you know, Maria did this analysis with the Rossby wave envelopes for both the southern and northern hemisphere, and yes, indeed, you see slightly less. I mean, when she did this K-means clustering analysis, and Maria, correct me if I'm saying something wrong, but essentially there's, yeah, it looks like there's less concurrent clusters in the southern hemisphere. So it looks like the continents and the topography in the northern hemisphere actually have a role to play in, you know, when exactly we have concurrent heat waves going on. So that's why I think the topography is important for you know, determining when we can get concurrent heat waves. The question is, but the question if this is a certain global wave or if this is local Rossby wave packets that just organize in essentially that just look like a certain global pattern, that one is still open.
Adrian, you have a question? Yes, we have time. So if you want to come here to speak.
Hi, it's just Adrian. I was just wondering, coming back to this question of the orography, that the IFS, one of the really big changes recently with the ensemble prediction system is this huge increase in resolution where everything is running at 9 kilometers now. I was just wondering, with this much better resolution of the you know, high terrain and so on, do you think you would expect to see any differences now in the performance of the ensemble prediction system? And might there be an opportunity using the reforecasts of the S2S to actually go back and look at the 2018 case and other cases between these two there? I don't know. I was just wondering what the perspectives were now for the new system. Now everything's running at high resolution.
Absolutely. I mean, I think we haven't done it for the new hindcast yet. So these are still the ones I'm showing here on the bottom right. These are still the old hindcast with the 18 kilometer and 36 kilometer resolution at longer lead times. But yeah, it'd be really interesting. I mean, I would expect, for example, for you know, for example, SST gradients to be much better represented, and therefore the jet stream over the North Atlantic to be better in terms of stationary wave bias. So you'd be, yeah, absolutely. We haven't looked, but it would be super interesting to check if it's better predicted.
Thank you.
Okay, thanks. Thank you, Daniel, again. And I think we can move on to our next talk. So we have Tiffany Shaw from the University of Chicago, who is going to talk about fast upper level jet stream winds get faster under climate change. And, okay, yeah, we do the share screen. All right.
Is it possible to use this?
Yeah, okay, let's try it. Oh, this one. Good. Let's try. Yeah, it works.
Okay. Thank you to the organizers for this great workshop. I'm really pleased to be here. I'm going to switch gears a little and talk about circulation extremes for their own sake. Okay, so circulation plays a role in heat waves and precipitation extremes, which we've heard so much about. Very important. I think an open question in the community is, how do we expect things like this, record-breaking jet stream wind event off the coast of the United States in 2019, how do we expect those types of events to change? That really motivated us to get into this, and it's in collaboration with my former PhD student, Osamu Miyawaki, who's now at NCAR as an ASP fellow. And you know, the fact of the matter is, for temperature, we have made really good progress. This very nice way of communicating the changes in extreme heat, or to think about a Gaussian distribution where we just add, let's say, 2 Kelvin as Daniela just suggested, and that really impacts the heat extremes. One way to think about and quantify this is to compare, as a function of the percentile, how the temperature is changing. And if we just add 2 Kelvin to every single percentile across the x-axis, and we ask how is it changing relative to the average, so how fast are the extremes changing relative to the average, if it's an additive increase like we just saw, then this is equal to 1. So everything is changing at the same rate, and extremes are not amplified. Now that's more or less what we see for temperature when we look in the CMIP-6 archive. This is the end of the 21st century relative to today in the mid-latitudes, which is where I'll focus my talk. And the multi-model mean is the black, and the shading is across the models, and it is pretty flat. So this is not just the schematic, this is pretty much what we see. And there is an amplification of heat extremes, as was mentioned by Simona yesterday during the session, over land. But that's a very modest increase, I would say. Now this is comparing, we can compare and contrast this with precipitation, which is really remarkably different. If we look at precipitation in the same way, percentile versus the response relative to the average, we see that extreme wet increases by 30 times the average. And what we know that to be a result of following work of Paul Warman and al. is this is due to a multiplicative increase that follows from the Clausius-Clapeyron relation, where you take what you got today and multiply it by 5% per Kelvin. And so this is really important because if you think about the distribution over here, precipitation at the tail on the extreme dry is 0, so 5% per Kelvin times 0 is 0. But over here, where you've got 55 millimeters per day in this daily distribution, 5% per Kelvin really ups the ante on extreme wet days. And so ultimately the question became, which we didn't have the answer for, is what do the circulation changes look like? Are they more additive or are they more multiplicative? And in particular, we'll start at upper levels because of all of the things we know and have learned about circulation change, the upper level acceleration is something I think we have the most confidence in. The question then becomes, if the average is accelerating, do we expect this to be lead to an additive increase, that the extremes follow the average, or this type of multiplicative behavior where the extremes increase faster than the average? And so when we went to take a look at what we would get from the same CMIP data, but now upper level winds, daily distribution, same 21st century, end of 21st minus end of 20th, what we saw is multiplicative. So the fastest winds over here increased 2.5 times the average. Slow winds are not increasing as fast. Now these slow winds, the distribution on the left goes from westward winds aloft, so this would be like a blocking regime, minus 20 meters a second to about 75 meters a second over here. So fast get faster, and the question is, at what rate? And in particular, if we zoom in on the 99th percentile, what we find as a function of latitude now, taking all longitudes, so there's no zonal average, all longitudes, all days at each latitude, the distribution at the 99th percentile is increasing in this 20 to 60 degree range at 2% per Kelvin. So slightly less than precipitation increase, but an important multiplicative value that we would like to better understand. So you can do something naive and say, okay, if I think this might be the way the real world works, and I take the reanalysis distribution and I just perform the experiment of multiplying that, so what we have today, by 2% per Kelvin, and I say, okay, 4 Kelvin at the end of the century, then I get this black line. And so armed with an understanding of the multiplicative increase, I can exactly say that this is why the extreme fast winds go up faster than the average. And it's not additive, which is, again, this flat black line. So where does the 2% come from? That ultimately is the question now. The first thing we wanted to check was that it was somehow robust, that it wasn't something, strictly speaking, in the most complex models, which is what I've already shown you here on the left. So we can look in a climate model hierarchy, which helps to unravel what physical processes might be responsible for this behavior. So the intermediate complexity would be to take an atmosphere general circulation model with prescribed sea surface temperatures, so take out the ocean physics. And when we do that and warm by 4 Kelvin, we see roughly the same rate of increase. So it doesn't have anything to do with ocean physics. And if we go further and take away the land, going to an aquaplanet, where we again warm by 4 Kelvin, we see roughly the same rate of increase. So we think this is very fundamental. There's something underlying this that doesn't depend on complexity. And another hint as to where we might want to go to explain this is to look just at geostrophy. So if you just look at the geostrophic component of the wind related to the Coriolis force balancing the pressure gradient force, we see the signature in that component. This surprises some people that if we take the wind at each day, each latitude, each longitude, each day, that we have this balance, and indeed we do. And so it tells us that we can try to understand and explain this behavior by using very fundamental concepts, particularly related to geostrophy, and then also hydrostatic balance, which would be thermal wind. So we decided to go for thermal wind to see if thermal wind could help us explain this. So what do we do with thermal wind? Well, we take the wind shear and we integrate it vertically from the surface pressure to the level that we are interested in, where we found the signal, 200 millibars. And thermal wind tells us that then at the upper levels, the wind is related to the integral of this density gradient, weighted by the Coriolis parameter and the radius of the Earth. Now, I've neglected the surface wind because it's an order of magnitude smaller, and that's something that we can show quantitatively, and it also follows previous work. And then what we need to do is understand how this density gradient is changing. This is the specific volume, the inverse density. And we typically then take a dry ideal gas approximation, and we say that density is related to temperature and pressure. But we're not going to do that here, because what we think might be at the heart of this multiplicative behavior is Clausius-Clapeyron, just as was found for the precipitation streams. So we follow some work of Kerry Emanuel's, and we instead write density for a moist atmosphere as a function of this quantity called saturation entropy and pressure. Saturation entropy is just an entropy that is conserved when we go from a phase change of vapor to liquid. It has a dry component, which would involve the warming of off, so this is not conserved. But then in combination with this Clausius-Clapeyron, we get this conserved quantity. And what Emanuel showed was when you write it this way, the thermal wind, the integrand becomes a product of two terms through a chain rule and through a Maxwell relation that allows you to think about the density contrast following the saturation entropy. So this is latitudinal gradients, and then how they get essentially rectified in the vertical through moist adiabatic adjustment. So this, armed with this, we can take the end of the century minus the present day of this moist geostrophic thermal wind and ask, what are the moist processes that might be influencing this? And the first thing we want to highlight is just this purely evaporative effect on the density contrast, what we call moist get moister. So what does that involve? Well, here's Clausius-Clapeyron in the black line, saturation, specific humidity with temperature. And because the wind depends on contrast, let's look at the contrast between the equator and the pole. It's very large, so the equator holds a lot more moist air than the poles. And if you just warm this temperature of both by 4 Kelvin, you see this steepening, which is this moist get moister effect. And the reason it happens is because of the multiplicative behavior of Clausius-Clapeyron. So 7% per Kelvin, if you multiply what you start with in near the equator, you get a big increase. But if it's 7% per Kelvin down here, you basically are at 0, so it's a very small increase. So this would tell us alone that we would expect the winds to accelerate. And I should importantly say this would hold even under polar amplification, something I'm happy to talk about. But what does this have to do with density? Well, once you steepen the contrast and you add a lot more water vapor near the equator, you make the air there lighter, because water vapor has a lower molecular weight than dry air. This is work of Dai Yang's. This incredible lightness of water vapor would lead to strengthening the density contrast near the surface through this evaporative effect. And when we quantify this in the data, what we find is this alone can explain the multiplicative increase, in particular this rate of 2%. for these fast winds. And that the other component, which would be in green here, associated with not only having the water vapor, but that the air then can rise and condense, which would affect temperature gradients in the vertical and temperature gradients in latitude, actually tend to compensate, because this would be a negative feedback due to increasing dry static stability, and latent heat release being more over the tropics and the poles gives you an increase of the temperature contrast. So that these two oppose, and at 200 millibars, what we find is they cannot account for why these tails are increasing faster at this altitude. And not only does that happen at the 99th percentile, if you look across the percentiles, the same kind of geostrophic moisture movement can explain the distribution change, it can explain the average change. So we think this is quite important for kind of opening up an understanding of how this extreme winds are multiplicative and not additive. So what does this get us? One of the things I'd like to highlight is these fast winds are important not only for jet stream transatlantic flights, but jet streaks are really important for severe weather, especially in the US, something that we're looking at. And so what this tells us is for every increment that we move into a warmer global mean temperature, we should expect to break records, in particular in the jet stream wind that we've talked about. But also, as it was brought up yesterday, this idea of a black swan, interestingly, Carrie Emanuel has also discussed this concept, but of a gray swan, to distinguish the fact that black swans are something we don't expect. We have no physical expectation for. Gray swans are something that we do have an expectation for. As we push into a warmer world, physical knowledge can tell us that we might expect more extremes. And in this case, he was talking about tropical cyclones pushing from category 5 into category 6, something that we can foresee by physics, but not through the historical record. And that's, I think, really important distinction between gray and black swans. So we wanted to look at what's happening now. I brought this up in the workshop before. I think climate change is here. So we took a look and found that in reanalysis, fast winds are increasing, but not in a statistically significant way. So the signal has not emerged. And across our model distributions for different emission scenarios in different hemispheres, these trends are within the model spread, which is good. But to ask, when the signal will emerge, you can ask when all of these trends are significant or filled in, and that's going to take another decade or so. So that's really the story today. I think it really brings to the forefront we need as a community to better understand what the circulation is doing for its own sake in terms of extremes, even just as important as understanding how circulation affects temperature and precipitation extremes. And there's a lot more work to do here, in particular to look at regional changes. So thank you very much.
Thank you, Tiffany, for this very nice presentation, and it's time for questions. Yeah, please, if you can come here. Yeah.
Thank you for a really nice topic. My question is, in your analysis, did you come across a climate model projection that had like a completely different result with the other models, and how did you deal with the result? Like, did you disregard that model, or you just took an ensemble mean?
So we didn't find a model that had an opposite sign trend, let's say as an example, or an opposite sign end of century projection. I think that was the most remarkable thing, that for many circulation changes, it's argued or thought of as being very uncertain, or there's lots of spread, but in this case, the models were in very good agreement.
Perfect.
Not only for the end of the century, but for modern trends, 1980 to 2022. So.
Okay. And also my other question is, have you done this analysis seasonally? Because I think this is just like annually average, long-term average. These results were not seasonal results.
So they were for all days. So
Okay.
but you can of course expect that the fastest winds would be in winter.
Yes.
And the gradients, as you would expect, is stronger. But we have subsampled the data into 2 6-month periods, and we see the same behavior in summer and winter.
Same
so
behavior.
This is not. I think based on the physical arguments, you would expect it to happen in those seasons.
Yes.
And that's what we see.
Okay.
Yeah. So
Okay.
thanks for the question.
Perfect. Thank you.
Any other question? Melinda? Yeah, I think we have time for one. But then, of course, I encourage you to discuss later on.
Yeah, thank you for a really nice talk. And my question is, when we were studying jet anomalies with Gabriele and comparing reanalysis with this MPI model, we noticed that the model does not represent very well the persistence in the jet, and also the jet going to extremely southern or extremely northern latitude and staying there for a while. So I was wondering if you consider this to be problematic in terms of knowing what will happen with the jet in the future, and whether there is a way to deal with this.
That's a very good question. We haven't looked at persistence in this paradigm. Every day is treated as its own day in the distribution. And we also didn't show the results. This was only for zonal wind. So we find very good agreement with these fast winds between the models and the analysis when we look at them in the right way. But meridional wind is something that we're still looking at. We do find the same arguments hold, but we also haven't looked at persistence. So that would be, I think, an important thing for us to consider. So thanks.
Yeah, I think these time scales are generally a problem for many models, getting the right time scales.
Yeah, certainly it's too strong, but yeah, persistence, I guess.
Yeah.
Weather regime, let's call it. Yeah.
Okay. Thank you again. We now move on to our next speaker, Wolfgang Wicker from University of Lausanne. Is going to talk about on the role of Rossby wave phase speed for persistent temperature extremes. Yeah, thanks. The floor is yours. I'm going to share. Well, first the share screen.
Yeah, thank you very much. Indeed, I will talk about the role of Rossby wave phase speed as a measure for flow persistence for the persistence of temperature extremes or heat waves. And I'm Wolfgang Wicker, I'm a PhD student at the University of Lausanne, and many people have contributed to this work. So I would like to start by recapitulating briefly a very common heat wave definition. And what you see on this plot here is a short temperature time series for the summer of 2018 in Lausanne. And we see quite a bit of variability, plenty of peaks that might be identified as a heat wave. Next, we plot the 90th percentile of the seasonally varying empirical distribution function to objectively identify hot days. So all the peaks above this orange line are hot days. But only those hot days that come in a set of at least 3 days, consecutive days, are identified as a heat wave, and we use this definition because it's related to impacts. But given that persistence criterion, I think it's quite natural to assume persistence of the temperature extreme requires an enormously persistent atmospheric circulation. But whether this is actually true, we wanted to investigate and check using the analysis data. In particular, we use a time series for summer of upper tropospheric meridional wind. And we chunk this time series into windows of 30 days. respectively. And for each of these windows, we did a space-time spectral analysis individually. So for each window, we get a plot where we have wave number on the y-axis and phase speed on the x-axis. And yeah, we have a time series of phase speed spectra. The climatological mean of these spectra is plotted here on the top row. So yeah, we have an increase in phase speed as we go to higher wave number. That's very much expected. And we use the centroid of this climatological mean spectrum as the boundary between a low and a high phase speed bin. And importantly, that definition of low and high phase speed now depends on wave number. Then based on the power for and the respective phase speed bins for synoptic scale wave numbers, we can classify each month as amplified slow, amplified fast, both of them, or on neither of them. And we use this as a categorical phase speed estimate. Once we've done this, we can do a composite analysis and check the role of phase speed for certain quantities. And what we see here in the lower two plots is the composite mean phase power spectral density anomaly, and very nicely illustrate the effect of our composite definition, that for the amplified slow, we have enhanced power of stationary waves with a close to zero phase speed, and for amplified fast, we have enhanced power for waves that have a phase speed of approximately 5 meters per second. That's very nice, but let's go into something that's more intuitive, more interesting. Look at results. So many heat waves have been associated with multi-week mean circulation anomalies in the upper troposphere, and the sentence here in quotation mark is meant to be a summary of literature. And we now want to assess what's the role of phase speed in creating multi-week mean anomaly. And the top row here shows the composite variance of 30-day mean meridional wind anomalies in the upper troposphere. So these are stationary waves that are not phase locked. They can have arbitrary phase and then appear in the composite variance. And indeed, as probably expected, we find enhanced power of stationary waves in the amplified slope composite. That's a consequence of our composite definition. If we look at the composite mean, however, of 30-day upper tropospheric wind anomalies, we find a similar magnitude for both composites. And the composite mean here is a stationary wave with a phase preference. So the troughs and ridges are phase locked to a certain location on Earth. And the finding of significant anomalies of similar magnitude in both composites was surprising to us, and we want to understand better what's the reason for this effect. We do this by looking at variability within those 30-day windows that are classified as amplified slow or amplified fast. And we do this by using Rossby wave packet diagnostics that assess meridional wind variability. And the top row here shows the climatological mean for summer of these characteristics. We have phase speed on the left and the Rossby wave packet envelope on the right. And yeah, phase speed highlights the location of the westerly jets over the North Atlantic and the Pacific. But there's also a latitudinal dependence with higher phase speed in the north of the northern hemisphere and low phase speed in the subtropics. The envelope itself is then also a depiction of the storm tracks. Looking at composite mean anomalies, we first see that the definition of low phase speed again holds with a reduced phase speed in the amplified slow composite, so the plot in the central row on the left column. But yeah, surprisingly, we see a little bit of an increase in subtropics in terms of phase speed. For the amplified fast composite, we see an increase in phase speed almost everywhere, mostly over the continents, or more strongly over the continents. But yeah, nice indication of what phase speed means in our definition. Looking at the envelope now, we find that the amplified waves in the amplified slow composite are found to the south of the climatological mean location of the storm tracks, whereas the amplified Rossby wave packets for the amplified fast composite are found to the north or in the same location, or wider range. Our conclusion from this is that phase speed is actually a proxy for the storm track position. It's not a very independent variable. It's not saying that the waves that just decelerated in place where they're usually found, but finding low phase speed means that waves have shifted to a different location, which then in turn can explain why we find a different stationary wave signal, different climatological mean wave in some sense. The plot that you've been waiting for maybe is the heat wave frequency. How do they respond to a change in phase speed? Our expectation was that we would see a dominant increase in heat wave frequency in the amplified slope composite, which is the upper plot of the two, which is due to the increased power and stationary wave activity. However, what we do find is that the response is very much zonally asymmetric, and the asymmetric response is also in a similar magnitude in those composites. And we think that the zonally asymmetric response is due to the phase lock stationary wave that we found in the composite mean upper tropospheric meridional wind, where we find increased heat wave frequency anomalies wherever there's a mean anticyclonic circulation, and we find a reduced heat wave frequency when there's cyclonic mean circulation. And this relationship between multi-week mean upper tropospheric wind and the heat wave frequency is more or less linear. In summary, to answer the question posed at the beginning, heat waves do not require an anomalously persistent circulation. In some sense, summer is very persistent anyway. And we found that the phase speed is, in our definition, a storm track position proxy, which will then in turn influence the phase locked stationary waves. And the strength of the mean anomaly in those phase locked stationary waves is more important for heat wave frequency than the persistence of the circulation expressed by Rossby wave packets or phase speed estimate. I think the outlook question then will be what limits the heat wave duration when the phase speed is stationary. So even if there's an anomaly with a zero phase speed, so it could stay the entire month, we usually don't find a heat wave that lasts 30 days, but still it's limited to a couple of days or a week. And with that, I would like to conclude, and I'm very happy for questions.
Thank you very much, Wolfgang. And any question? Let's see also online. Jacopo? Sorry.
Of course, I get a question about the spectrum.
Yes.
No, it's just very nice, very clear. Two questions actually. One, said there is a 30-day time window to compute the spectrum, and I was wondering how then the resolution of the quasi-stationary wave is affected, because I see that the spectrum is full; it doesn't have any gaps. So
Of course, the window length very much depends frequency resolution, and it's not the 6-hour resolution of our initial data, but it's the window length that determines phase speed resolution. You're right, the shorter the window, the lower resolution. And we've chosen 30 days here to ensure decent resolution, but also a large enough sample size. And we found things get noisy if we go to longer window lengths, and we need to start using some filtering to get rid of noise. And yeah, we have no gap in our spectra, so we do find something that we call a stationary wave, because the individual 30-day windows do have a time mean that for sure it's not exactly stationary, but to the extent of our frequency resolution is identified as a stationary wave. And therefore we have no gap as it's sometimes seen in spectra where we have.
So you do have the simple Fourier transform of the time to get the spectrum at 0 meters per second.
Exactly.
Okay, it actually matches. Like I thought of doing Quasar, it matches quite well. It seems like it's quite a smooth transition. I would have expected that at 0 there is more like a little jump because of that.
Yeah.
And there is no interpolation there.
No.
Oh, okay.
It's
Great.
just a timing. And yeah, for context, we have also a paper about the role of phase speed for waves, and I think everybody uses a different definition. And in our case, phase speed is a proxy for storm track latitude, and I think in your paper, phase speed is a bit of a proxy for the strength of planetary waves versus synoptic scale waves. So I think your very nice paper is another example for showing that phase speed is an independent variable.
No, indeed, actually, my second question was on the, sorry, that's very short. There is a 2D map of phase speed. How do you compute that one? Is Flacolidis or?
Exactly,
okay.
That's following the obvious diagnostic.
Lenka, you had a question.
Yeah, so thank you for the answer. I'm just wondering, in our slide, you showed the
10:30.
it was the
11:30.
Mm-hmm.
when you look at the map that is previously inside fast response with the spectrum, do you have an explanation for that?
If we can maybe go to the slide, but yeah, like no, I don't know whether Atlantic or Pacific behave differently in terms of the Rossby wave packet envelope, and I'm not quite sure why they should. But in terms of phase speed, I find that the response is very nicely symmetric around the globe. But yeah, I'm not quite sure what your question was targeting.
In the plots, it looked like the one of, I don't know if you're on yours, but the Pacific.
Sorry, Lenka, can you speak up? Maybe come closer to the mic. Sorry.
So I was just wondering, can we go back to the slide of the map? You still have it
Slide 5.
between.
I think if you can
So the one that shows the phase
PowerPoint
speed
and then
ones.
slide 5.
Yes, like was
Yeah.
this one?
Yes.
Yeah. So.
No, we are slide 1.
Oh, sorry. This one.
This one, yeah.
Let's see. So, oh yeah, I guess yeah, maybe I just yeah, actually it seems to be more symmetric than I remembered, so it doesn't matter. Yeah. Okay.
Yeah, but I'm happy to discuss offline more of the specific details.
Okay. Yeah. So I guess I didn't see them up properly. Yeah. Okay. Thank you.
Yeah, thanks again for Wolfgang, and I think for the sakeness of time, we now move on. And of course, if you have other questions, then there's a wrap up and conclusions and the coffee break, and you are encouraged to continue the discussion later. So now we move on to Jana Strigunova from Uppsala University, who's going to talk about the signatures of Eurasian heat waves in the large-scale Rossby waves in reanalysis and CMIP models.
Okay, thank you very much for your presentation, for inviting me for this workshop. And yeah, let me share my screen and go to presenter mode. And okay, let's go over this. Now, can you see my pointer? Yes, you can see. Okay, so let's start. Yeah, that was quite interesting to see that Wolfgang showed that we don't need persistent anomalies in large circulation, but I might give a bit different perspective on how global Rossby circulation is connected with Eurasian heat waves. And we'll start with a typical view on this aspect. So usually we consider Rossby waves as a part of blocking, which in synoptic scale to be considered as large-scale anticyclonic persistent anomalies, which then lead to atmospheric other atmospheric heat driver to heat waves, or in specific case, Eurasian heat waves. But sometimes this local phenomenon, as we consider heat waves, can be to a large extent on way more broader area. And in case of Russian heat wave, we saw that it was very big area of Eastern Europe and Western Russia affected. And in this sense, we ask ourselves, what if these large anomalies, they also can be translated in anomalies in blocking, which are already anomalous state, and then in some specific configuration or some signatures in Rossby wave anomalies. So the question what I try to answer is, how do global Rossby wave statistics change during Eurasian heat waves? And here I pose two questions. First is similar to what I mentioned before, but I just want to point out that heat waves as regional phenomena seems to appear in planetary scale troposphere barotropic Rossby circulation. And I also will give an overview on how these signatures are represented in CMIP models. And I will start with discussing what kind of data sets I used. For the first part, I used reanalysis data sets, and I would like to point out that only extended boreal summer considered in my analysis. We have all reanalysis gridded on the same, interpolated on the same grid with the same number of vertical levels and 40 years of daily time series. For the second part, I used the subset of CMIP5 models, and I would like to point your attention that all of them have different horizontal resolution, different vertical resolution, different top, and then it leads to different truncation. I also will discuss briefly difference between historical and AMIP simulations. So let's start a bit talking about the tool of what you have been using, and thank you to Nedelka Jagar on Tuesday for introducing the mod software. I just would like to give example how actually we did it for heat waves, and I will start with showing this typical map of wind field at 500 hectopascal with composite only presented during Russian heat wave, and we see, for example, these winds which look like blocking or stationary structure. What we do in our analysis, we take this field along with gap potential height field in different vertical levels and transform or project them into a series of half functions or half harmonics, which is shown as example here. Of course, we do also in 3D, and this is what we call vertical vertex extraction, which then coupled, and as an outcome of this procedure is half coefficients, which in the end are 3-dimensional. I will not speak really a lot about this coefficient, although they're quite interesting, but I would like to speak that we can compute actually global total energy from these half coefficients. Here, I would like to point out that this total energy is sum of kinetic energy and available potential energy, or therefore it's mechanical energy for the whole global circulation. But we're mainly interested in their anomalies, which are obtained as multi-annual means and then normalize it. Here, I also would like to point out that on these steps, we do separate from each reanalysis and model. In the last step, I obtain climatological PDFs where they combine all these time series together and then within some specified zonal wave number ranges. And here, what I mean under planetary scale waves, it's zonal wave numbers from 1 to 3. I will speak mainly about these climatological PDFs, just showing robust features across different datasets. And I will not speak much about identification algorithms, since Welcome already pointed out that it's exceedances of certain percentile. In this case, we use 95 percentile. But what is important that these days I was using in my study to separate from climatological PDFs and really see how it's different or not different from what is typical state. And now we're coming to result part, and again, heatwaves local phenomenon in global barotropic planetary scale circulation. I will start talking about climatology, and interestingly, we found that energy can be described via chi-square distribution, and therefore, when we analyze anomalies, we see that there is skewness apparent, and it's not zero, implying that its distribution is not Gaussian. What is most interesting that this feature holds not only for planetary scale, but for other parts of circulation, what we analyzed. And now the question, how does it change when we consider only circulation during heat waves? We find quite interestingly that probabilities of positive energy anomalies, which on right tail, are found to be increased. And this also implies that there is an increase of probabilities of extreme of energy anomalies, which then can be translated in different message that skewness increases, and which we found to be statistically significant according to bootstrap procedure. Now the question, of course, how does it actually translate to our real world or grid space? And here I show only era 5 as example, but it's the same for other analysis. We start with climatological state, where only Rossby waves and troposphere part, barotropic troposphere part only is presented, and we see some anomalies going on around approximate region of Northern Europe. What we see that during heat waves, this anomaly seems to be amplified, and it's quite different compared to climatology. And this aligns quite well that the more energy anomalies in distribution in global PDFs, and more amplitudes seem to be on planetary waves. Now I'm coming to the second part of my talk, and I will speak mainly about how to CMIP5 model represent these features. First, I will talk about climatological PDFs, and we see that shape itself resembles, and here we again consider separately historical simulation and EMIP simulation. In both cases, there is a similar shape, but there is difference in mean. In particular, there is difference in tails, which then can be closely seen on quantile to quantile plot, where on the y-axis there is CMIP5 quantiles, on x-axis we analyze quantile. And we see quite well alignment on average quantile, while some outliers are to be seen on their upper and lower distribution, part of distribution. And according to Kolmogorov-Smirnov test, I found that distributions are not statistically significantly different. But what we find when we consider this change in skewness or in distribution, that models actually do not reproduce this increase in skewness. Of course, for some models, it might see that there is some spikes or some bumps, but it's not that robustly represented as for reanalysis. And in case of uncoupled simulation, there is some tend to be shifted in intermediate energy anomalies. When we also did the same exercise for physical space maps or composite maps, and we see that for historical simulation, we observe the same pattern during heat waves, but these anomalies do not really different from climatology. There is nothing changing in circulation. But then we look again and uncoupled simulation, and it seems to be a bit more robust feature, although on lesser energy anomalies. And this actually, this is showing similar result as ERA 5 and other reanalysis, that there is a really intensive anomalies going on around where heat waves are observed. And then again, it's the same feature showing that this is deviate similar to what ERA 5 and other analysis show. And now I'm coming to my summary. At first part, we saw that yes, heat waves being local phenomena have signatures in global Rossby circulation, which then can be seen as increase of probabilities of positive energy anomalies, whereas also increase of skewness or distribution and increase of amplitudes of Rossby waves. For the second part, we saw that models partly reproduce wave patterns, but amplitudes are weaker for coupled simulations, while while uncoupled runs or only EMIP models show similar amplitude to reanalysis and patterns, although both of them do not show significant change in skewness of PDFs. And now I'm coming to my last slide, and here I show only results for planetary scale, but in the first paper we discussed how really heat waves show signatures across different parts of circulation, and we also discussed zonal mean flow and synoptic scale, which show a bit differently as planetary scale. And now I'm working on the second part of this topic, and I'm happy to answer all your questions. Thank you.
Thank you, Jana, for your talk, and there's room for questions. Valerio.
Hi, Jana. Thank you for the nice talk. I have a couple of questions actually, and related to each other. The first one is, given that there is such difference between AMIP and CMIP, how this relates with what Ivan B was showing on the first day of this workshop about the influence of SST variability on, Rossby waves. And the second question was, did you try to have a look at CMIP 6 models as well? And in case, what do you find?
Well, it's really hard to give a clear answer for your first question. I mean, yes, we use the same metric, but we used a bit different framework that he performed some model simulations with different experiments while I was taking control simulations and focus on how they represent circulation. I mean, I assume if we would work more in collaboration, then probably we would also focus on SST bias, because yeah, there is a certainly difference between these two runs, which usually considered to be connected with some not well representation of SSTs. Coming back to your second question, so I haven't really mentioned two-meter distributions here, because it was not that in context of this presentation, but what we did, we found that this temperature distribution, at least at surface, they align quite well, and it's the same hold for CMIP 6 models. We did not perform results for circulation part of decomposition. But yeah, it would be interesting, although according to recent literature, there is no significant improvement in blocking representation or Rossby representation from CME5 to CME6. So I honestly would not expect something bigger improvements in performance for these models.
Thank you. Any other questions? Lenka.
Hey Anna, thank you for the talk. It was great. I was just curious, I don't know if this is related, but looking at the PDFs of global temperature or even hemispheric temperature of observations that I briefly presented in my talk, it looks like with warming, the skewness in observations does change in that PDF. And then what Tiffany showed in the models, the skewness doesn't change as much. Do you think this kind of mismatch between observations and models is what's reflected in your PDFs here as well?
That's a good question. So I can also relate to part of my analysis which I didn't show here. I plot the same PDFs for my temperatures over Eurasia, and I found that there is a clear shift in all models and all reanalysis, but of course, when we go to circulation, things might not mean the same as surface. And clearly, these results on skewness show that there is certainly something missing in the link, which we think is represented in models.
Okay, thank you.
Okay, thanks again, Jana. And we now move on to our next speaker, who is Christian Graf.
Just
Hey, good morning, everybody. Can you hear me well?
Hi, Christian. Yes, we can hear you.
Okay, so I start sharing my screen. Just a second. This one. So you now can see the screen as well?
Yes.
Okay, so let me start. So yeah, yesterday evening's discussion basically sparked some thoughts on what established basically highly amplified Rossby waves and associated extremes. And in particular, like we saw in yesterday's talks from Vera, but also now from Wolfgang and Jana, that these extremes are always embedded in very intense geopotential height anomalies, or ridges. And when you look in the literature, for instance, I like a lot the work by Brian Hoskins and Tim Woolings, who basically showed theoretical concepts on how Arctic amplification might result in highly amplified Rossby waves. And what they show is that it's essentially if mid-latitude heat source remains the same, then reduced baroclinicity and reduced zonal winds might result in more amplified Rossby waves. And this mid-latitude heating is usually near the western boundary currents, where the storm tracks are and where you have a lot of latent heat release. And other work already showed that a latent heat release in such ascending airstreams are first order process for the establishing and maintenance of blocking life cycles. This is work by Stefan Pfahl a couple of years ago, and then further corroborated by Dani Steinfeld. And my own research in the past was on the extratropical transition of tropical cyclones and investigated how this results in downstream impact with highly amplified Rossby waves. And basically, there we could show that the Rossby wave amplification on atmospheric dynamic scales involves a complicated scale interaction ranging from the condensational processes in clouds via warm conveyor belt ascent, its outflow, phasing favorable with the jet and amplifying a ridge and triggering downstream development and eventually leading in hemispheric Rossby waves pattern, which are amplified. And this depends upon the phasing of weather systems, and this was heavily explored in Jacobo's PhD work. So when today, I look out of the window, you see north of the Alps, it's a little spell of wet snow, so we are here. But this is also embedded again in a blocking situation with blocking over Greenland. So you see here the omega block, and there is integrated water vapor transport into the Arctic. So basically you see here divergent wind, which inflates this ridge. And this is basically the scale interaction that is difficult to predict. And in 2 weeks ago, we didn't know that we would have this cold spell here. So, and to more exemplify this process, I show now results from that work with Heather Archambault a couple of years ago, where we did more a generalized experiment of this extratropical transition impact on the waveguide. What you see here is a weakly amplified waveguide in blue, and a tropical cyclone in the West Pacific approaching this waveguide. And we show air parcel trajectories which ascend. You see an outflow channel in red. This is at high levels, blue are low levels, and you see vertical ascent in the tropical cyclone. I animate this in a second, and then you see the tropical cyclone approaches this this region here ahead of the trough, and then a ridge builds and triggers downstream development. A secondary cyclone evolves, another warm conveyor belt, ultimately leading to a very highly amplified flow situation over North America downstream. So here you see now the ridge building, trough amplification, downstream cyclone, another warm conveyor belt inflating this ridge. So this is basically a chain of processes from cloud condensational processes to the hemispheric Rossby wave pattern. And now my talk is about to show how this synoptic weather activity really matters also for recent heat waves. And this is work which we have done in the large-scale dynamics and predictability group at KIT. Mainly Annika, Julian, Moritz, Josh, and Serafin and Jan were involved. And also our colleagues at ECMWF, Linus Magnusson, Magdalena Balmaceda, and Frederic Vital. And I already have a spoiler here for the North American heatwave 2021. This shows the PV structure in upper levels. You see this highly amplified ridge, and the crosses show warm conveyor belt air masses that inflated this ridge and contributed to its strong amplitude. And the second event I briefly talk is just 3 months ago, an omega block situation over Europe, and I talk to that at the end of the presentation. So this North American heat wave, we have talked a lot in this workshop already. So this shows the 2-meter temperature anomaly, which was incredibly high, more than 15 Kelvin above climatology in the region. Lytton is marked here in a box around it. And we see here in black the omega pattern over the region in the 2 PVU contours, so very highly amplified flow, and the red contour encompasses the potential vorticity anomaly associated with this ridge. And when we look at the prediction of the air mass over the region, here in this case, I mean, I agree with what Daniela showed, that we had guidance on subseasonal lead times for a warm spell. So this shows the ensemble distribution for the peak of the heat wave of temperature at 850 in this box around Lytton. There was indication it's well above climatology, so model climate is shown here. However, there was a predictability barrier, so there was a step when the ensemble shifted after the 22nd of June only towards the actual observed extremely very high temperatures, which were way out of what the model climate thought it could be. So there's really a predictability barrier, and once you overcome it, you can predict the magnitude of that heat wave. And we investigated that more in terms of what made it so difficult to predict it, and distinguished good and bad forecast members in all of these ensemble simulations in terms of representing the upper level ridge structure. And there you find that bad members basically occur before this 22nd of June. So before, like with more than a week lead time, we couldn't represent the ridge. And only after that, in a week lead time, we could predict the ridge amplitude. And this is shown here with a plot showing in shading the temperature error in the bad forecasts. So basically, the bad forecasts not only underestimated the ridge magnitude, but also the temperature consequently. So this would be the analyzed ridge. And in this, the ensemble mean of this bad forecast just has a zonal flow, and no temperature anomaly here, but rather an underestimation of the actual temperatures. Whereas the good forecast after 22nd of June they correctly represented the ridge structure and do not have a temperature error anymore. And now we computed backward trajectories from that region, from the ridge, and we find basically, again, this is the color shading 10-day backward trajectories. Red is at upper levels and blue is at low levels. The air mass that was injected into this ridge emerged just before the heat wave from the Central Pacific. So we had some ascending airstreams immediately before the heat wave injecting into the ridge. But then more than a week before, 10 days before, we had this emergence from the West Pacific of an air mass that was injected in the upper troposphere and ended up over the region. And looking then more into how this was represented in the good and bad forecasts, I show here more a synoptic chart. So it shows again the waveguide in the analysis in the solid line. We have roughly 5 days before the peak of the heat wave, we have a pre-amplified flow, which is also represented in the bad forecast shown in dashed. And this is due to a very high tropopause high indicated in yellow. However, what happens on the Pacific, on the West Pacific side is that we have this warm conveyor belt outflow impinging on the jet. And this is here indicated by the green contour. And in blue, we see that this outflow is not represented in the bad forecast members. And when we go 3 days further, we see now an amplified flow pattern. So in the analysis, we have this downstream trough, downstream of the initial warm conveyor belt activity that amplified. We have new warm conveyor belt activity further inflating this ridge. And again, this warm conveyor belt activity is not represented in the bad forecast members, and the flow is more zonally aligned. And then going closer to the peak of the heat wave, we had another burst of warm conveyor belt activity, further maintaining the ridge. Again, this is not represented in the bad forecast members, and the flow remains zonal. So to wrap up this heatwave 2021 in the Pacific Northwest case study, we kind of also show that what we know, that the heat dome develops under an extremely highly amplified upper level ridge. We see there is a predictability barrier for the predicting this ridge roughly a week ahead with a week lead time. So earlier it wasn't possible, and consequently we couldn't predict the extremely high temperatures. And we could show in this study that it was this chain of synoptic events with favorable phasing of unusual warm conveyor belt activity in the Meyu-Bayou front region, going ahead of a trough and triggering downstream development that helped amplifying this ridge in this extreme amplitude. And if you want to learn more details, Annika led the study and it's out in GRL. So now coming to the blocking situation just 3 months ago over Europe. Early September 2023, we see this omega pattern in geopotential high 200 hectopascal. And on the upstream flank, we had this cutoff cyclone, and early in this event, it caused flash floods locally in Iberia with severe damage. Then within the omega block, we had a record high 0-degree line measured over Switzerland in the radio sounding of Payerne, and this was the second highest on record. And the record was just hit 2 weeks before with another heat wave, and there was this late summer heat wave, not very extreme temperatures, but still unusually hot temperatures. But the most devastating impact was downstream a couple of days later when we had another cutoff and this Mediterranean cyclone Daniele developing, first heavy precipitation and damage in Greece, but then this deadly floods in Libya with thousands of deaths because this was really unexpected and extremely high precipitation. So this was a real compound event over Europe, and again, we want to look on how predictable that was. And when we compute backward trajectories now from the core of this ridge in the upper troposphere, just 5 days backwards, again, the color shading shows red in upper levels. We see they emerge and ascend all from this cluster of cyclone activity in the West Atlantic at low levels 5 days before. And when we look at synoptic charts, what happens here is, so this shows potential vorticity. The red would be the waveguide, and then in addition we see mean sea level pressure, and we have 2 tropical cyclones in the West Atlantic. In particular, tropical cyclone Franklin moves into the mid-latitudes and triggers a cyclogenesis near Newfoundland, and then you get initial ridge building in the West Atlantic. And this really becomes strong and builds a massive ridge over the central Atlantic. A cutoff cyclone forms. These floods in Iberia are triggered. And when we look at a warm conveyor belt trajectory, this ridge was really inflated by ascending airstreams which emerged from all the two tropical cyclones, the Newfoundland cyclones, and we have this massive air mass injection that inflates an upper level ridge. And eventually we get anticyclonic wave breaking of this outflow air mass over Europe. The cutoff cyclone cuts off and the PV streamer and downstream cutoff cyclone forms over Greece. Looking at the predictability of the event, now exemplified here in terms of the 3-day precipitation over Greece. So this would be the model climate here in Syrian, the maximum the model climate knows. The truth was double the maximum the model knows. And again, we see on subseasonal lead times indication that we have heavy precipitation in the upper part of what the model climate knows. However, again, only the magnitude of the precipitation was only captured in a week lead time after this extratropical transition occurred. So here's really around a month change. We had this interaction of the tropical cyclones with the jet and this ridge building going on, and then the model knew it would be a very extreme case. There is climatological evidence for this diabatic contribution.
You have 1 minute left.
Yeah, to blocking over Europe. So this is work by Serafin Hauser. I come to the almost final slide. We now have a warm conveyor belt metric which allows easy identification of warm conveyor belts also in climate models. So this is free to download. We applied it to subseasonal models and see systematic biases in warm conveyor belt outflow, and this goes along with problems in predicting blocking over Europe. And likewise, this activity is sensitive to the ensemble configuration, in particular the stochastic physics perturbations in the IFS model. So with that, I leave it with this key point. So I think there's a need for the correct representation of the multiscale interaction related to synoptic dynamics, and also potentially very large ensembles in order to capture these unlikely interactions of synoptic dynamics with the large scale flow, which are rare, but if they happen, they can result in these highly amplified flow patterns. Thank you.
Thank you very much. Thanks, Christian. And any questions? Yes, please.
Hi, thanks for the interesting talk. I was wondering, could you maybe go back to, I think it was slide 13. That was a bit quick for me to grasp, and I don't know whether the question still stands when I see the slide again, but yeah, exactly. I was wondering when and where did you start those trajectories? Because I'm looking at similar situation myself, and I was really confused to see that none of them come from further south, or
yeah, I mean,
Africa.
These are started here. Basically, the black dots, they are very dense. They show every 25 kilometers in that area centered over Payerne, Switzerland, in the upper troposphere. So they are started between 300 and 200 hectopascals, so really near the tropopause. And then 5 days backward, we see they are first advected with the jet very quickly here. But they ascend in this Newfoundland cyclone. So the blue shades show they emerge from low levels and all ascend and are not advected at upper levels. So like this is really exemplary of the air mass that is in the upper level ridge.
Yeah, okay. Yeah, that explains, because the trajectories that I'm looking at end up not at 200 hectopascals, but lower down. Yeah, thank you.
Any other question in the room or online? Lenka.
Hi, Christian. Good to see
Hi,
you, and thank you
Lenka.
for the talk. So that was very nice to kind of outline the effect of the kind of misrepresentation of the kind of insufficient ridging in the models, how that leads to heat waves.
and how that can be related to perturbations from outside of the extratropics. I guess this is more like a discussion question, but say in climate models, since we know that we are not representing tropical cyclones and perturbations like this sufficiently, so they are too weak and too many. What if we had a case where, what if we did actually get the tropics right? How much would the response of the extratropics and the stationary waves, how much would that improve? Is there a way to quantify this, or do you have any thoughts on this?
Yeah, we like long-term experiments where you would where you would suppress that effect. I mean, there's case study evidence in the study from Dani Steinfeld and Stefan Pfalay. They did like 5 or several case studies suppressing the latent heat release in the ascending airstream, and they see less amplified flow patterns. In the work that Moritz Steinhardt did, we also show that there is a less amplification of the global Rossby wave pattern when you have weaker warm conveyor belt activity. This is because of the perturbations you do. So I think you do not fully need to resolve cloud physical processes, but you need to basically have enough synoptic activity, and that can be achieved by perturbation schemes like the SPPT or SPP scheme. So that enhances warm conveyor belt activity. So you would need to have an experiment where latent heat release in these regions is suppressed to actually quantify it. But there's a lot of case study evidence now in that, and in particular this early work that I did with Heather, we have a no warm conveyor belt scenario and see that the flow is really less amplified in a more general sense. So that might contribute to the general underestimation of the two-solar flow in models.
And do you have a sense of how much that would contribute to the overall improvement of the large-scale planetary circulation in the climate statistics, like in the biases?
No, I can't say there a number. Yeah.
Okay, thank you.
Okay, thanks, Christian. And we now move on to Hung Lee from University of Chicago, who's going to talk about the upgradient eddy potential vorticity flux, the role of non-quasi-geostrophic and non-adiabatic effects.
Ora si registrerà la conferenza.
Thank you.
I hope you can see my screen now.
Not yet, but something seems to be happening.
Oh, wait.
No, not really.
Share.
Oh yeah, now we
okay.
see it. We see also your next slides. Have you? Well, that's is it right? Well,
yeah, we see the
we see the presenter view. Try
so,
maybe to share the full screen to see if.
Wait. Okay, maybe something now.
Is as before. Now it works. Yeah. So.
Oh sorry. Okay. Wait. Sorry. Okay, then somehow my. Okay. Okay. So now it works. Yeah, so thank you everyone for still showing up, and also thank you to the organizers for organizing this really interesting workshop, and thanks to all speakers. I really could learn a lot. I'm really regretting that I cannot be with you in person, but I just recently became a father, so I have some family duties. Okay, so in this talk, I will talk about propagation pathways of Indo-Pacific rainfall extremes and how these are connected to the large-scale circulations. Just to give you a short motivation, when you look at extreme rainfalls during the South Asian summer monsoon, for example, last year in Thailand and in Bangladesh, we had very heavy rainfalls occurring exactly at the same days. And of course, these two single events, this could be random coincidence, but when we also look at this statistically, we see that rainfall extremes, they can occur simultaneously over large spatial areas. And this, we also know from previous studies that this interseasonal variability of rainfall extremes, These are heavily dominated by the boreal summer intraseasonal oscillation, which is the summer counterpart of the more famously known Madden-Julian oscillation. And what also is important, so this is now plotted here as a single event. And what you see in blue, this is the occurrence of rainfall extremes. And this is a classical BSISO event and how it propagates. And so you first see, okay, this is connected to the occurrence of extreme rainfalls. And second, what you can see, okay, this gives you somehow a forecast horizon of about 3 to 4 weeks. So understanding better the propagation of this BSISO and its connection to extreme rainfalls offers the opportunity for S2S forecasts and also early warning signals. Okay, so this talk is mainly about better understanding these propagation pathways. This is the first part of this talk, which is mainly about what we recently published in an article in Nature Communications. In the second part, I will a bit broader the view and look also about how rainfall extremes can connect different monsoon systems between India and the Sahel on daily timescales. Okay, so what do I mean first when I talk about extreme events? So we define extreme events locally as top 10% of wet days in June, July, August, September. And then we apply a measure which is called event synchronization, which basically really measures the synchronization of rainfalls between large spatial scales. I can't go into detail here, but if you're interested, just look in the paper or ask me later. And what we find is these 6 spatial regions. So hatched areas mark regions that are left out because there are hardly any rain. And we find these 6 regions, or what we also call them communities. It means, okay, within such a community, rainfall is likely, or heavy rainfall is likely to occur kind of synchronously. And so we have Equatorial Indian Ocean, we call it Bay of Bengal, Maritime Continent, South Asia, Western Pacific, and North India, China. And when we then look deeper at it, we see a certain propagation pattern also of rainfall extremes. So rainfall extremes that start in the Equatorial Indian Ocean, and then we follow them in time. They propagate around other 5 over the Bay of Bengal, Maritime Continent, South Asia, towards the Western Pacific. So we see a certain propagation pattern. And when we plot the composites of these events that start in the Equatorial Indian Ocean, we see that these propagate towards the Western Pacific, and this shows the classical BSISO propagation pathway. However, the problem is when you look at single events, not all of these single cases, so this is composites, but when you look at single events, not all of these events show this classical propagation pathway. So what we did a clustering of these different propagation pathways. We used outgoing long wave radiation because it's a bit smoother. So for the clustering algorithms, it's a bit easier to work. And we apply this clustering on Hofmöller diagrams in zonal and meridional direction over the Indo-Pacific domain. And zonal and meridional direction because the BSISO, it travels eastward and northward. And then we find actually quite 3 well-distinguished propagation modes. Oh, come on. Yeah, I hope you can still see them. I don't know why it's now broken. Previously it was working. We find 3 different propagation modes. So a first mode that we call the canonical mode, which basically shows a clear propagation in zonal and in meridional direction. And this propagation is kind of the classical propagation of BSISO, but we find also a second mode, which is called the eastward block mode. And this eastward block mode, how we called it, it's kind of block this propagation around the region of the maritime continent, but it travels northward. And there's a third mode, which has an initiation in the Equatorial Indian Ocean, but it quasi remains stationary there in this region and hardly travels neither northward nor eastward. And then we ask, okay, what is the reason for these 3 different propagation modes? Yeah, sorry that this is now broken. And we looked at these different samples when the propagation occurs, and we looked at the SST background state of these different propagation modes. And when we first looked at the canonical mode, yeah, we actually hardly see any particular pronounced anomalies in the sea surface temperature fields. However, when you look at the eastward block mode, you actually see a quite strikingly La Nina pattern in the equatorial Indian Ocean. And when you look at the quasi-stationary mode, you see the opposite. You see a quite strikingly El Nino-like pattern. And yeah, so I won't go into the mechanistic details, but we could show that then this ENSO kind of changes the moisture background state, and the BSISO normally follows a certain moisture background gradient. And this then at the end leads to these different propagation modes. Oh my God, it's now everything broken. I'm so sorry. I was actually looking only at this area in the Indo-Pacific, and now we broaden a bit the view, that we look also at the synchronization that happens between North India, and what we see is that there's also synchronization from North India towards the Sahel zone, and we now try to understand this connection better. This is so far unpublished work, and also still not 100% sure what exactly the mechanism is. So I will show you some ideas that we have, and if you have also seen something similar, I'm very happy to discuss or get in contact later. Okay, so we have the synchronization between North India and the Sahel zone in terms of extreme rainfall events, and this synchronization is not instantly, but this synchronization happens kind of lagged, so with a maximum lag of 12 days. So the kind of, on average, the highest synchronization you find when you have rainfall extremes in North India, and these are likely to be followed 12 days later in the Sahel zone. And the synchronization is not every year the same. You have some years that have quite strong, so this index measures the synchronization per year. And you have some years where you see a quite strong synchronization, and you find some years where you hardly see any synchronization. So you have a quite high yearly variability. And it's also not every day the same in the summer month, but you find a clear peak of when the synchronization happened from kind of July to mid-August. Okay, so which is kind of the core monsoon season in North India. And how this synchronization looks like is shown in this animation. So you see here outgoing longer radiation again, because it's a bit smoother than precipitation, but this is how this propagation looks like from North India, and it travels towards, quite clearly it travels towards the Sahel zone. So we have kind of three candidates that contribute to this mechanism. And the first one is what we think it's about the tropical easterly jet. So what we did, we were looking at, okay, we were correlating this index that defines the synchronization to the upper level U200 anomalies on daily timescales. And this reveals the pattern on the left-hand side and shows kind of strikingly this strong correlation to the area of the tropical easterly jet. And when you look at the V200, so the meridional winds at the upper level atmosphere, you see some negative correlations over North India, so which kind of indicates we have something like a southward displacement of this jet. We also looked, okay, in which years is it stronger, in which years is it less strong. So we
you have the 2 more minutes.
Yeah, fine. I'm finished in one slide. So you have this yearly variability again. And when you look at years in which you have strong synchronization, you have something like a La Nina background state. And if you have less synchronization, you have something like a background state, which shows an ENSO, El Nino state, which is kind of clear because we think it's the classical background state by La Nina, which brings more moisture towards India in the monsoon time. So we have these two factors so far, the strong tropical easterly jet and the La Nina background state. And what we also see statistically, and we don't know how this yet works, is when you look at the BSISO, the BSISO has certain phases, and so the blue bars shows the likelihood that you find desynchronization based on different phases. And you see for certain phases, you see a quite strongly enhanced likelihood compared to a respective null model. So this is kind of what we've done so far. These are my summary slides. If you have any idea how this connection between India and Sahel zone works in detail, please contact me or discuss with me. I'm very happy to discuss. And just 10 seconds of self-advertisement. I'm looking for postdoc positions. So if you have any, please contact me as well. Thank you for your attention.
Thanks very much, Felix. And now we can take questions. Jacopo?
This teleconnection, especially compounding extreme, is very interesting. Thanks for the nice talk. But I was wondering if you had a look at the role, if the equatorial waves can play a role to explain this propagation of the extreme from India towards the Sahel. And maybe even if you're looking at OLR data, you can check maybe the Wheeler and Kiladis spectra to see if there are some Rossby, Rossby waves, equatorial Rossby waves happening. Like, have you checked, or do you think?
I have checked. I've not found any. Maybe I have applied the wrong measures because it's not always easy to find these patterns. I have checked for Rossby or Kelvin waves. I couldn't find any pattern. I was also, actually, I was thinking, okay, this is probably a Rossby wave. And I couldn't find any, yeah.
Okay,
but yeah, I'm really happy. If you have any other ideas. Yeah.
This tropical, sorry, the tropical easterly jet is like the southernmost branch of the monsoon anticyclone. It's the southern edge of the monsoon anticyclone, right? So is there a relationship between, like, if the monsoon anticyclone is stronger, then you also see this other connection more, and then also the monsoon overall is stronger? There's also this type of connection.
Yeah, I think this is somehow how it works. At least that's what we've tried to show is this in the statistical thing when we showed, okay, we have a strong tropical easterly jet, you have a La Nina background state, and you have BSISO in certain phases, then you find these really enhanced likelihoods of the synchronization. So I think these three factors really modulate it, but exactly how this works, I don't know yet. I'm really happy to discuss this further. Yeah.
Thank you, Felix. I think we have to move on to our next speaker, Chaim Garfinkel from the Hebrew University of Jerusalem, who's going to talk about the precursors of extreme summer heat events in the Eastern Mediterranean, role of the Mediterranean sea surface temperature.
Hi, do you see my screen?
Yes, we can.
So let's.
If you try to put into the presentation mode.
Yeah.
Okay, perfect. We can see and hear.
Okay, great. Yeah, so thanks for this opportunity to present. So today I'll be presenting some recent work I've been doing on the large-scale drivers of heat waves in the Eastern Mediterranean. This is work that in collaboration with Derrida, Arfad, Asaf-Khan, and Ronit, and I'll be describing a paper that's currently in review in Quarterly Journal. So the key question we're interested in is how far in advance heat waves are predictable, in particular in the Eastern Mediterranean. And part of that is to understand the precursors of these heat waves. And so, yeah, so that's what we're looking at. And the previous work has highlighted some possible precursors, for example, the weakening of the Asian monsoon, low from the west, maybe changes in precipitation in the Sahel. Less appreciated or less investigated the role of sea surface temperature variability. And we're also interested in the relative role of subsidence versus horizontal temperature advection versus diabatic heating for these heat waves. So yeah, so and I'll be presenting now is using the analysis data and observational data. Going forward, we're also interested in models and how trustworthy model predictions are for heat waves. So yeah, so here I'll be talking about analysis and observational data. And for those who are less familiar with the summertime climatology in this region here, so there's a pronounced trough, South Asian monsoonal trough over India, and this trough extends into towards the Mediterranean. In particular, this sort of tongue of the trough over Iraq is known as the Persian trough, at least here, and this extension of the Persian trough also includes a little tongue into the Mediterranean here. Associated with this trough here are the occasion winds. These occasion winds are associated with or lead to northerly winds, northerly winds that attract relatively cool air, maritime air from the Mediterranean over the land regions that are adjacent to the Mediterranean. And what I'll be just discussing here is, so that's what happens in climatology. What I'll be discussing here are the role of this for heat waves. And we also have, the Asian monsoon, South Asian monsoon, and also monsoonal precipitation over the Sahel. This is omega 500 hectopascals, and we have rising motion over the Sahel in South Asia, in East Asia, and subsidence over the Eastern Mediterranean. And so we're interested in understanding. So this is the timing, and we're interested in understanding how these various fields change and evolve in the lead up to heat waves. And these are just additional metrics of the monsoon for OLR, diabatic heating, and divergence. So we see in all three of these metrics pronounced influence of the Sahel and also South Asia monsoons. And so, yeah, so we identify heat waves as follows. We use the EOBS data set, and the EOBS data set incorporates about 27 different stations over the Eastern Mediterranean in Israel, specifically in Israel. As compared to the rest of the Eastern Mediterranean, their station data from the 50s. That's in the EOBS data set from these various stations. And so the coverage is, I think, among the best for the Eastern Mediterranean of any region in the Eastern Mediterranean over Israel. So I'll be focusing on Israel in this talk, but the maps I'll show later include the entire Eastern Mediterranean. And we define an extreme. So if each of these 6 polygons that are shown here with these red lines, we average the surface temperature within each of these polygons, and then we look at, we define 95% threshold for each polygon as well, and then we look at exceedances for at least 3 consecutive days in May through September. And it turns out that we end up with a list of events. Many of the list of events are the same. Many of the events are common for the different polygons in this region here. For example, this particular event on the 7th of August 1998 is common to 4 of these different regions here. In general, as you may expect, there's certainly a tendency for there to be more events in the more recent period and fewer events in the more distant past. So essentially almost no events in the 80s, only a handful of events in the 90s, and then in the past 20 years, many more events. And many of these events are known to overlap with significant impacts over Israel and adjacent countries as well. Yeah, so what I'll be doing now is going through how each of these fields, the anomalies of each of these fields, and they lead up to heat extremes, these heat waves. And I'll start off with the true potential height at 1,000 hectopascals. That's this slide here, and this is starting on the top right here. This is the shading here are the anomalies and true potential height at 1,000 hectopascals. The day after the onset to 3 days after the onset. Here is 2 days before the onset to the onset date, 6 days before onset to 3 days before onset, and this is 10 days before onset to 7 days before onset. Here I'm looking at the mountain region, but it looks pretty similar for all the regions. And for this particular region, we have 21 events that we've identified. And so if you look at this top right panel here, so after the event has already begun, we have a weakening of the Persian trough. So that's all here. We have this Persian trough here near the surface. So this is weakened. especially over Iran after the event has begun. So with this color shading, and the black contours show the temperature anomaly itself. So we found temperature anomaly over Eastern Mediterranean, not much else going on elsewhere. So they seem to be relatively focused and not really compound with other regions. If you go backwards in time, two days before to the onset date, we see this Persian trough really extending all the way from South Asia towards Iran and into Iraq. And if you go 6 to 3 days, it's still there, but it's getting weaker. And then 10 to 7 days, it's not there at all. Instead, what you have in these earlier leads is a low over the Atlantic. It propagates eastward, and you see this warm anomaly here already over Iberia and southern France 10 to 7 days before. That then propagates eastward and certainly amplifies by quite a lot as a temperature anomaly amplifies associated with this Persian trough weakening here, and weakening of the Caucasian winds. So that's for the lower troposphere, what you see. If you look at SSTs, the anomalies in SSTs, there's not much going on in SST anomalies 10 to 7 days before that in the Eastern Mediterranean. However, you do see large anomalies in the Western Mediterranean and also East Atlantic and Central Mediterranean as well. And these SST anomalies then propagate towards the east, and then as you get closer to the onset of the event, reach the Eastern Mediterranean and peak at essentially 1 degree warmer SST anomalies than typical, and this is on subseasonal timescales, so it's not a general warming trend. It's subseasonal warming of local SSTs contributing to heat waves. And then the last thing is the monsoon. So it's the contribution of the monsoon. So I'm adding in three more rows here. This is omega 500 hectopascals, OLR, and diabatic heating from 400 hectopascals to 700 hectopascals. And I'll be focusing on this left column here. So in the 10 to 7 days before the onset of the heat wave, we have a weakening of the climatological upwelling over India, over South Asia. We have higher values of OLR, which correspond to weakened convection. And we also have a reduction in the divergence that typically occurs over South Asia as well. And we see this 7 to 10 days before the onset of the heat extreme, and also 6 to 3 days before as well. And so the net effect is that we have a weakening of the Asian monsoon. And if you look sort of during the onset itself, it's more or less gone. So it's really a precursor signal, and then it's more or less, it's been reversed if you look on the onset, after the onset itself. So we've identified so far, I guess, a series of possible precursors: weakened Persian trough, a low from the west, warm SSTs in the west and central Mediterranean, and a weakening of the South Asian monsoon. And so the next step is to understand whether there actually is sort of predictability from these various precursors. In particular, the next step is we've identified events that have a warm Western Mediterranean and a weakened monsoon. And there's 37 such events that are separated from other, so sort of a period of time where we have warm SSTs and subseasonal timescales in the Western Mediterranean, simultaneous with a weakened monsoon. We identify 37 such events. We also identify 31 events with a cold Mediterranean, cold Western and Central Mediterranean, and a strong monsoon over South Asia. And there's 31 such events. And then we take the difference in surface temperature over these various polygons. And that's what's shown here. So this is the coastal region, the mountain region, Dead Sea. And it turns out that if you look, let's say, a couple of days before the onset of these events, there's essentially no anomaly. And then over the next 10 days or so, a week or so, we have a rapid warming. The temperatures rise by 1 degree, and then they stay warm for over a month afterwards. We see these temperature anomalies that persist, and these sort of significantly warmer when you see the bolded lines. And you see this for all regions, not just these three. These are a couple more regions have added in. And so whenever you have this weakened monsoon and warm Mediterranean, you have an actual precursor signal for anomalously warm conditions that persists for a month, and you do a shift in the PDFs as well. And so there actually is some predictability associated with this. So predictability on subseasonal timescales is associated with the warm SSTs and South Asian monsoon. So the final part of this talk in the paper is the relative role of horizontal temperature advection versus subsidence versus diabatic heating. So to diagnose this, we've taken the temperature budget and try to close it using ERA5 data. That's what I'm showing here is essentially the temperature tendency equation, and the horizontal temperature advection term, the vertical term, and the diabatic term. And what's shown here on the top right, in the top row is the temperature tendency itself. This is 6 to 3 days before the onset of the event, and this is right immediately before the onset of the event. And then this is the top row, and then this row shows the sum of these three terms. And so certainly the local details are not right, but the large scale pattern, we are closing the temperature budget relatively well, and sort of capturing at least the large scale features, with residuals being on sort of smaller scales. And so we can then separate these three terms into three components, so the vertical, horizontal, and diabatic term. And it turns out that the horizontal term is doing pretty much everything over the Eastern Mediterranean. The vertical term has a small impact over Iraq and Iran, this region here, but over most of the region here, it's really the horizontal term that's doing most of the warming. And diabatic is, if anything, is actually giving you a negative tendency, negative feedback. And so we can then take this horizontal term and decompose it further, and in particular focusing on this term here, which is like, so here the primes indicate, the bars are the time mean and the primes are the deviation from the time mean. So what this term in this box here indicates is the deviation from the time mean of the winds and the climatological temperature distribution, which is associated with the weakening of the Acasian wind. So when you have the Persian trough weakening, the Acasian winds also weaken. And so the U prime, the V prime are also weakening as well, or negative in this case, or opposite the climatological direction, and you end up with a weakening of the Acasian winds, and that this term specifically is shown in this bottom row here. And so it turns out that this bottom row is, especially during the onset date itself, or right up to the onset date, is doing most of the warming. And so yeah, so it's mainly this weakening of the Acasian winds that's giving you the heat wave over the Eastern Mediterranean. So some conclusions, yeah, so the heat waves, at least in Eastern Mediterranean, are preceded by robust anomalies 7 to 10 days before the onset of the event, which maybe is longer than the typical horizon for weather forecasts. If these precursors are present, then there's a significant warming over the following 10 days that then persists for weeks and actually over a month afterwards. These precursors include a weakened South Asian monsoon, warm west and central Mediterranean sea surface temperatures, and a low from the west. The horizontal temperature advection is a dominant process leading to the extreme, and it's really within the category of horizontal temperature advection, it's the weakening of the Acasian winds that does most of the work. And that's it, yeah. And so this work is currently under review. Thank you.
Thank you very much, Chaim, for your nice presentation. And now there's room for questions. Yes, please come. If you can come here, so people can listen better.
Hi, Chaim. How are you? Just I wondered about the vertical advection. Which level you used here? Because I know this area is very complex topography.
Yes.
So, yeah. So what about the vertical advection? The levels there that you used?
Yeah. So you're right. There is complex topography, and it's a little bit difficult to. Yeah, you're right. I mean, so I think I know you talked yesterday about So I think So in particular, that's also the region where you have climatological, like if you go back to climatology, that's the region where, the climatology is also a little different as well. Like there's over the Eastern Mediterranean, there's subsidence. Over here, there's actually rising motion in the climatology. So I think the dynamics could be different. In other words, if you look at the anomaly in this region here, over this sort of northern Iraq region, it's mainly associated with this panel here. Yeah, so there's actually a bit of so the climatologically there's rising motion. There's actually subsidence, and you see that here as well. A very strong subsidence. So there's a subsidence. There definitely is subsidence in that region here, which helps give you this pronounced warm anomaly. So over that region, I think the subsidence is doing some of the work. But at least over the regions with less topography, I think that then there it's the horizontal term that's doing most of the work.
Okay, so given that we are running a bit late, I would thank again Chaim and then move on to our last speaker for today and for this workshop, Federico Grazzini from ARPA Emilia Romagna. And so sorry that I opened workshop. So Federico, who's going to talk about boosting extreme rainfall forecasting using non-local large-scale predictors. So Federico, the floor is yours.
Hi everybody. So we are talking now about precipitation, so it's slightly something different with respect to heat waves, but still kind of something driven by large-scale, as we will see. This work is has been made in the framework of the transregional.
Sorry, we need to share the screen for those online.
So I'm not sharing?
No.
Okay, but in the meantime, I will.
Yes. Sorry.
So in the framework of waste weather, so it's the German Transregional Collaborative Center, and with some also partners like CNR-ISAC and Archive. So some words of introduction, and following what we were also saying yesterday about heat waves. So this kind of extremes are extremes by definition, but also are something recurrent in our climate, and in particular, I will focus on the Mediterranean climate and on, in particular, in northern and central Italy. So they could be generated by different physical processes. This is another things to have in mind. But most of the time, we can see that these processes are tightly linked with the large scale. And another interesting thing is that although precipitation is still really difficult, quantitative precipitation, of course, also for this stream, but we demonstrated in a paper we did with a colleague of CNR-ISAC that we have a better skill in predicting the large scale condition driving of this stream compared to normal conditions. So again, it seems that there is a hint that we have a kind of specific path that can lead to the stream, and so you are kind of a bit facilitated in predicting those events. I just put here some preliminary work in which myself and other people in different groups identified specific synoptic precursor of extreme precipitation over northern and central, over the Alpine region of northern Italy. And I mean, to start with, the group of ETH has been for a long time looked at this, identifying a kind of precursor in terms of PV, and then I did a similar thing in terms of analogs in terms of potential height and pressure, and also Martus and Al again in terms of PV. So it's quite clear that those extreme precipitation events are tightly linked with a specific synoptic pattern that see a wave sitting, a Rossby wave basically sitting over the Western Mediterranean and triggering some intense southerly flow impinging over the Alps. We went more into the details of this Rossby wave, and we saw that those Rossby waves were put in place by a wave packet propagating from remote region. And as I said, that extreme can be generated by different processes. We tried to separate those processes in three main categories that we call category 1, category 2, and category 3. And we identified specific precursors, specific wave train precursor for each of these categories. And the category are related to the type of process, as I said. So category 1 is a more like extreme associated with the passage of the frontal of the front. Category 3 on the opposite side is more like weakly forced convection, so in which also the Yarnell cycle plays an important role. And category 2 is a sort of in between where you have embedded convection in a head of the frontal passage. And I want to comment this because this is not really the theme of the presentation. It's just to set up a kind of framework. And now the real thing of the presentation is, can we use, so once we see that extreme precipitation events are different on their own, but they share a common drivers, okay, at different scales. So can we use this precursor to, in a kind of predictive mode, can we use those drivers we have identified to improve the precipitation forecast? And this is basically about it. So what we did is we defined a kind of data set of extreme precipitation events from 1961 up to real time. And so we made kind of based on some criteria of extreme. I don't have time to go too much in detail. Then we knew also from previous studies as it showed that those extremes are linked to a specific local situation with a wave, with a strong water vapor transport. And okay, and then we added another point that to look at the more large scale dynamics, not linked to the local, not only considering the local scale, but also looking at even a broader time and space horizon. So defining what we call non-local large-scale dynamics indexes. And especially on this, so the new thing concerning this is together with people in KIT, this was a nice contribution of Joshua Dorrington, and we developed a kind of framework to define those non-local index. So you define your event definition. So you create a time series of your events, long time series. You select the relevant field that you think can be associated with this, and this say software produce a composite of the precursor fields of the variables that you select, doing some significant testing and removing areas that are not connected, so you do quite an accurate thing. And then you can take the real-time fields you want to use and project those fields onto this precursor composite and get a scalar index that is telling you how your instantaneous field is similar to those precursors. So now we have all the elements to try to put together all these elements. So non-local indexes, local precursor, and direct precursor. When I say direct, we try to use also the direct model out of precipitation of models. So we take all these elements in a kind of, so here we have a list of all our precursor, and we try to, with the machine learning, with two models of random forest, to estimate, given a field, a forecast, if tomorrow, for example, will be an extreme precipitation day over this large extended region, and if yes, to classify according to this predefined types of extreme we have identified in previous work. And you see, we have different class of precursors, as I said, no local, climate, direct, and local. So one first nice result is that if you look at the future importance of this different class of precursors, so here we grouped the precursor in classes, as I said, you can see that as the intuition will tell you that the more you go at long time ranges, the more importance are taking the no-local indexes. So the no-local indexes, it's weighted more in the system because it's more predictable. While the direct model output of the precipitation is dropping relatively fast in terms of weight. That means that the model see that we lose ability to get a correct prediction, and the local predictors are going down, but not as fast as the direct model output. And the climatological ones are just giving a little bit of help at the real end of the thing. So I'm going fast to a couple of examples. So we are running this kind of system pre-operational at Arpanet. Still has to be improved, but anyway, I mean, it's already interesting the way it does. And so every day for each initial conditions for each forecast, basically, we produce a kind of graph like this with 10 days of forecast. This was the one issued the 12th of May, and on the 16th of May there was this big large flood in Romagna. So on this graph you see the probability of having an extreme from two kinds of prediction. The standard ensemble prediction of the CNR-ISAC, so the empty gray bars, is the probability directly computed from the ensemble to have an extreme or not, so to go over some threshold. And the equivalent of the Malcox, so the random forest system, is the one in color. And it gives, you can have different colors because also it is telling you the kind of extreme. So in this case, there was a kind of a little bit higher probability estimate at the range of day 5 compared to the ensemble. And the reason why this was like this is because one of this non-local index was showing really high value. So and this you see, so the predictability barrier in this case for this index was like 5 days before. If we look at a similar graph for precipitation, we see that we started to have a good precipitation 3 days before. We go to another case, again, kind of similar results, to introduce a nice really thing that you can do with machine learning is that once you set up your model, using some specific function, you can also gain knowledge of what your model is doing and why your model is predicting this a given result. So in this case, we use the Shapley additive explanation that is basically telling you why you got this result. So which were the most important contributors to have this decision. And in this case, for example, was the direct model output that was already pushing for this, but with some addition also of the integrated water vapor transport at local scale, and so on and so forth. And finally, another nice feature we produce with this is a kind of in this diagram this is showing the intensity of the events that you are trying to predict and comparing the intensity in terms of area extension and total volume of rain compared to all the other events we had in the data set. We are talking about 900 events. And so it's not only telling you a kind of a classification or a probability of having an event or not, but also in a quantitative way what could be the extent of this event. So to conclude, Malcox, this system provides a complementary way to predict extreme precipitation and probabilities, leveraging on the status of the large scale. Verification is encouraging. We need some more, of course, time and cases, and then also we need also a better tailoring. But the nice thing is that you can, especially the estimate of these non-local indexes is ready to use for other people. The Domino package is available, and you can configure this package for your region, specific region. It's not really tied to only Northern Italy. Okay, thanks.
Thank you, Federico, for this nice presentation. And if there are any questions from the audience or online.
I have a very super quick question. If the domino package, can you extend it to consideration of other extreme events?
Yeah, because once you give the list of your extremes, so
it could be anything. Okay, great. Thank you.
Any other question?
There is online.
Yes, please, if you want to speak.
Yep. Hi. Hi, Federico. Very important. I have a couple of questions. First, I wanted to ask what type of model is the machine learning model used? Is it a neural network? Or is it
random forest?
I'm sorry?
Random forest. So we use two different models of random forest, one in series of the other.
Okay. So random forests, are they producing at the end calibrated probabilities? So, for example, if you check for specific years, it's okay. But if you then check the probability distribution over the last, let's say, 20 years, are they really calibrated towards, what we would expect?
Now, okay, so you can those we don't use a calibrated probability. You can calibrate your results. So there are further models to apply to calibrate your result. In our case, I did some tests, and I think we didn't need to calibrate.
Okay.
Because
and
the calibration is already done through the training bit. Yeah.
Yes. Yeah, I was just wondering whether there was a post-processing, because usually in this model, I mean, for the random forest, you wouldn't get this kind of calibrated probabilities. That's why I was wondering that. And so the last is that in the feature importance, I can see that basically it's two predictors only that are separated from the rest, because the rest of the importances are pretty similar for the other predictors that you use. And so I was wondering whether using only the two first predictors, whether you check that makes it simpler and leads to better predictive skill, for example.
Yeah, that's an important question. I spent really a lot of time to try different configuration, remove some predictors, and keep only the more relevant. But at the end of the time, at the end of the story, I kept those 10, even though some of them are not so important as others, but they are still adding some value in some cases. So that was my kind of final list. But you can spend months and months in trying which is the best configuration, not only of predictors, but also in terms of metrics for judging the goodness of your system, and also it depends also a lot on the metrics that you use.
Right. Thank you.
Okay. So I do not see any other questions. So thanks again, Federico. And we can also thank all the speakers of this morning session. We can give them an applause. Thanks to everybody. And so this was our last presentation. So now there's some time for discussion. And Valerio, do you want to? Yes, do you want to? Shall I? Can I?
Sure. Why don't you go ahead and?
Okay, I was not prepared for that.
Can I start with the comment?
Of course.
Sure.
Yeah. So one thing that I noticed in these days is that maybe I'm a bit redundant on what I said already on Tuesday, but it seems that when it's time to diagnose wave packet, we have a lot of diagnostics. For example, we've seen the envelope, we've seen local wave activity, we've seen the waveguide, but when it's time to see what's the origin of the wave packet, what is this vorticity source that you see in the upper troposphere, it seems to me, at least to my knowledge, that there is so the picture is a bit more hazy with respect to the pure diagnostic tool that we have. And so the thinking in this sense, so we have seen, for example, Jacopo shown that when you've got these bursts of wave packet, so one cause may be an enhanced baroclinic zone over North America. But this morning we've seen, for example, the wave packet that Daniela was showing, responsible for the heat wave. It was really also extended in the meridional. It seemed to be originating in the tropics and then emanating through this great circle up to to Europe and the extratropics. But we cannot really state clearly what is the origin that what's the cause that really at the tropopause produces these vorticity source. Am I in a certain sense right? So do we need some more understanding and improvement in this sense, or there are existing theories and tools which allow us to clearly state what's the origin of these wave packets? So, for example, in terms of non-conservative processes, latent heat release, or just conservative dynamics through baroclinic instability. Tiffany.
Sure, yeah, I think that's a really great point. And one tool that comes to mind, I didn't hear about it at all this last few days, is by Sarishnook and Hoskins' beautiful paper, and I think it was 87, where they define the Rossby wave source. Okay, so how divergence generates rotational flow, and I think that would be a great target to just look at, because I think we might be missing some tropical perspective here for some of these packets, especially when you're talking about predictability on beyond a week. There's got to be something that.
So probably the diagnostic community should look back to these, let's say, milestone papers and try to apply this theoretical concept and deliver maybe a tool which is amenable to data, even high resolution data, and all the output that the models and the analysis can give us, and try maybe to deliver a tool that also can tell us something about the origin of these wave sources. So yeah, that could be a point, common ground to do some research, probably. Yeah.
There is already so I think that goes back to the point I was sharing. This particular diagnostic. You can find SB with SB so we can this is already in this.
So probably in this sense, like having like a common repository for wave packets analysis would be great. As for example, the climate modelers, or evaluation. But when you do model evaluations, so for example, there are some existing packages with all the diagnostics are collected in some place. But probably if we look at the wave packets and wave dynamics, this is a bit missing. So probably more. We can do a bit more and maybe joining forces and make these tools that perhaps in some cases are already existing, put them together and advertise them.
So by a quick Google search, Rossby wave source is within WindSparm, but I think that you're making a great point that maybe it would be nice to centralize somewhere all of these tools that might be useful for the community. And it was a great point, Tiffany. I really think it's something that would be really nice to explore.
Any other inputs? Yeah, Jacopo.
About the Rossby wave source, just a little comment. And there is in It's about the role of surface temperature anomalies inducing Rossby wave source. Lately, in some manuscripts, in some papers I've seen, there is some authors say that the presence of surface temperature anomaly, like during a heat waves or anomalous heat, this one can directly affect the upper level circulation and maybe enhance the reach there. I think there is a bit of problem of causality because we cannot use the temperature anomaly at the surface, which is probably first order induced by the circulation, okay, excluding the soil moisture, etc., as a somehow a causal link to connect the bottom and the top, because the Rossby source connects the divergent part to the rotational part, but it starts with the divergence part in the upper troposphere. So we have to get the process that manages to bring this extra energy from the surface to the upper troposphere. And if we have something like that, like in the tropics, it's convection, and then we have it. In the mid-latitudes, it's not so obvious. So even the connection with SSTs or the connection with the surface temperature anomalies, we have to work a bit on understanding better the physics that brings this surface anomalies of energy to the connection to the Rossby waves. For the convection is obvious. Totally. We'll have a master thesis on that next semester. I'm looking forward to that. That's very fun.
I would like to comment on this part, if it's possible.
Yes, of course.
Yeah, I mean, that's actually coupled with my way of thinking on this picture, and actually I wanted to comment on it further on, but since Jacopo pointed out, yeah, I mean, how we would imagine that we have certain chain in events or physical process which leads to this, but of course, on what time scale this happening processing, because I would think that, okay, we have certain anomalies occurring in tropical region, we then translate it towards exotropics and then mid latitudes where we get that some enhancement and local feedbacks. Therefore, with this chain of events on different temporal spatial scales where it's a bit comprehensive to understand, and yeah, we need to have a common effort really to understand where it comes. And I saw several presentations where it highlighted that we need to go through this different scale interaction from larger to smaller, from smaller to larger, to really trade this chain of events.
I think I personally liked, very much the approach that at some point Christian was showing about the Lagrangian backward tracking of water content, I think it was, in the extratropical transition. And I think this could be extended in a systematic way into the energetics and energy fluxes and latent heat fluxes particularly to better assess the role of the tropics for the Rossby wave packets and the wave trains that are formed. I think there are tools for that. Just that maybe they could be collected.
Yeah, you mean something like extend the Lagrangian trajectories that were used, for example, to explain the ridge building in this sense to a whole wave train or a whole wave packet in a certain sense, rather than the single phases. Yeah.
Different particles in the Lagrangian wave.
Yeah. Christian, please go ahead.
Yes, thanks for the suggestion. So, I mean, before Jana made a good point, it's difficult to disentangle these scales on which the ultimate amplification occurs, because I think this what I showed, the one conveyor belt, is a very specific scale on the synoptic scale. It's not necessarily that the air mass is fully connected all the way down to the highly amplified flow. So like I showed for the Pacific Northwest. So it can also have an intermediate role in amplifying the flow upstream and then triggering downstream development. So it is not that, I mean, the Lagrangian assumes that it's the same air mass that ends up in a ridge, but this is not necessarily the case. It was the case in the 2 case studies I showed now, but there are other cases where it's a different air mass at the end because of downstream development. So that requires basically this, scale-aware diagnostics to say, but I think also the Rossby wave source is a good starting point, because the essential action also from the synoptic scales is the divergent outflow, and the Rossby wave source basically accounts for this divergence in the upper troposphere, and you see it in tropical convection. You might need to adapt the vertical height to properly see it in the extratropics, but I think that metric could work also across scales.
Yeah, thanks, Christian, for this input. Some more comments or ideas from the audience, or even the audience who's attending online?
I mean, to be honest,
sorry.
No, I mean, okay, no, I just wanted to suggest some practical action. Okay, that's great. I mean, I was wondering whether we could open I don't know, a collaborative document where, I mean, we report on what we discussed these days, and we try to highlight some common thoughts and some take-home messages, but mostly call to actions on some specific topics that we can contribute all together.
An action plan to move this forward.
Might be good to have some platform where to share lecture tools as well. On the website.
Yeah.
Come together from different disciplines.
Yeah, Christian, do you want to add something?
Yeah, just a comment. I mean, in order to capture these unusual, very highly amplified events, I mean, we need large ensembles to actually capture them, because they are rare, but they are often within the scope of internal climate variability. And because they are rare, it's difficult to assess how they change also in climate change. We need large ensembles to get these unlikely but possible interaction across scales.
So Christian, aren't the existing large ensembles good fit for this? Because there are.
Well, I come from the weather prediction side, so I haven't worked with climate data yet. I just know that what is around in terms of subseasonal reforecast, operational forecasts, often recent extreme events in the forecasting sense are out of the model climate that we know from these models.
Yeah, but there are large ensembles of climate model simulations run starting with the same model, the same forcing, just starting from different initial conditions so as to sample, to separate kind of the internal variability from the force response. So that could also be a...
It could be.
Tiffany?
And to get back to typicality, the most extreme events, of course, are really destructive, and we absolutely continue to focus on them. But if we go down a little bit, percentile, there's still a lot to be learned, I think, in leveraging more events and trends that we see in events that just cross our culture. How is it connected to these other large-scale trends that we're seeing? There's still a lot to learn, even if it's not most 99% percentile event.
And I wanted to go back, sorry, then it was more a question for Tiffany, because you brought up more than one time as part of the discussion the circulation trends that seem to be driven by aerosols, but that hasn't really come up as part of this workshop. Are you talking about the work by Sutton and his group. Is that the work you have in mind? Yeah. For summertime European, what kind of the the difference between the Atlantic versus the European jet? Is that what you had in mind?
Status is, before we get to there, there's very clear trends in geopotential height.
Yeah.
From high intense work that Kai said.
Yeah.
And that's more stationary. So
Okay.
we're seeing these high pressure anomalies that again look like physicality sitting over Europe, sitting over Western US, and what those are driven by, how they're related to these trends in heat waves that we also see in the exact same region. I think it would be really interesting, and then there's emissions around aerosols and how that's connected. I think there's room there to
connect that piece, yes.
Yeah.
Jacopo had a comment, and then Melinda. Sorry, did I miss something?
Actually, given that Tiffany was talking about typicality, one thing that strikes me of the presentations of yesterday and today was that, so the good nice presentation of Melinda about the instanton and the idea that these very extreme events could be more predictable. It's very nice, it's very theoretical to present it, but today we heard both from Daniela and from Federico that actually we see this signal also when we look at the actual forecast. And so there is a nice matching between this abstract idea and the operational results. And that's what was very nice. And then a second point, a bit unrelated, it's again on the waveguide aspect. After seeing all the talks during these 3 days, it seems like there is a bit of a shift towards more normal waveguides. Like many talks talked about wave packets that are propagating and about a waveguide that is the more usual vorticity gradient or the jet stream, and not necessarily about about stationary waves circumglobal on a double jet waveguide, which were more like they contributed a bit to the debate about the connection between heat waves and Rossby waves in the past. And seems to me, but maybe I don't know if Kai is connected or somebody else has another opinion. There is now, from the talks today and in the previous days, there is more of a shift towards a more normal waveguide, a more usual somehow waveguide. And and last thing, sorry, this predictability, this extra predictability, back to the instanton again, seems due to Rossby waves. So to the fact that we have a remote, so again, Rossby waves are important for heat waves, also from the predictability aspect. So yeah, these are two things I bring home for sure from the workshop.
Melinda, do you want to add something?
A comment on typicality and on the other extremes, which might not be typical. Of course, the typicality is one part of the picture, right? And I think it is good to know about it. It can be really useful, and it's also nice to see that indeed sometimes one can see supporting results related to predictions, and I think this should be pursued forward as well. But as Tiffany mentioned also, of course, we shouldn't forget about the less extreme events, which then are also very important, can have impact and can be more heterogeneous, thus more difficult to predict and to understand. And also these also very extreme events, it can happen that some atypical events happen. So these events are then even less probable, these super extreme typical events, but the probability is not zero. So it's good to remember that the big picture is always more complicated, and and we shouldn't forget certain aspects.
Valerio, you had one comment. Yeah, a bit related to that. I don't know. I'm a bit puzzled now by using typicality as a synonym of predictable, because I mean, I saw from some presentations yesterday that there are some typical patterns that are actually not so predictable, at least in a canonical sense. So either because I mean they are forcing some local aspects that are less predictable, or because I don't know, models have biases in that. And yeah, I was wondering if this offset is something that we should work on, or I just completely misunderstood the whole pattern. It's more of a question to the specialists.
Any ideas about this?
I mean, of course, there is no one-to-one connection between like certain aspects of typicality and predictability. So it can be a hint that certain things are better predictable, but it doesn't have to be always the case. And then it can happen as well that as events are very multidimensional, it can happen also that certain things are typical and then other things are not typical. And even if something is typical, it doesn't mean that it's typical on every time scale. So if like tracking back the event, for example, in time, you might get some good predictability in a certain time period, but that might disappear or get very bad for other time periods. So
it's more like a diagnostic vocabulary versus prognostic vocabulary.
Yeah, but what I mean that it's not like if you have a typical event, you can it's super clear that you can predict it very well. But, yeah.
Would it be fair to say that's the predictability is like the typicality of the precursors?
Yeah, yeah, the typicality of certain precursors. Yeah. But also that doesn't mean that some anomalies still, like if you don't see this typicality of the precursors, that certain precursors cannot lead to the event, right? So these are only the most probable precursors, and in that sense.
Okay, so I don't want to interrupt this discussion that can proceed further at the lunch, but also, of course, offline after this workshop, hopefully. Valerio?
Actually, there is one point that I want to make before we go offline.
Yeah?
The collectibles.
Yeah, sure.
I think it would be nice if we get out of these, as many people have discussed about it, with an hypothesis of having this community together again at some point in the future. If someone is willing to, I mean, take over what Bologna did this time, I don't know. Does it make sense?
Yes, of course. I think that so we've seen such many interesting things during these 3 days, and it would be a pity not to continue this work. And so, for example, one thing that we were saying before was about writing a document on what we have and what might be improved, maybe advertise better what we have, and stayed a bit hidden maybe these days, and so promote what it is already available, and yeah, of course, continue to discuss about such interesting topic. And perhaps Valerio, since you organized the conference, you want to and Simone, of course. Sorry.
Yeah, no.
And,
Before we conclude, I wanted
yeah.
because there have been a couple of comments online, so I wanted to make sure that at least they're read out loud. So David is saying, talking about packages that can be implemented in the framework of Rossby wave detection. Also, the Rossby wave ray tracing algorithm has been implemented several times as a way to explain the effect of toroidal force instrument latitude climate variability. And Kai adding to Jacopo's comment, time scales are crucial here. It seems to me that when moving from hourly to more climatological scales, waves tend to increasingly behave as theory suggests and can be circumglobal at times. And then he says that he would be happy to contribute to benchmarking tools that compares different metrics. So I just wanted to make sure that his thoughts were communicated to the broader group. Yes.
Thank you, Kai.
And I hope, yes, Kai gets better. We missed you.
Okay,
yeah,
well,
so I just
yeah.
wanted, well, first I just wanted to say that from my perspective, it's a very successful workshop. I really, really thank everybody for the great talks, the great posters, and especially the great interaction. I think this was really maybe the best part. I mean, of course, the talks were great, but also the fact that it was just really, yeah, everybody got involved into sharing their thoughts and ideas as to how we can make progress. Again, I'm relatively new to the community, but if this were to become a regular event, I would definitely be very happy to keep participating. Yeah.
Yeah,
and so thanks for everybody to make the time to be here, both in person and online.
Yeah, thanks, and thanks also to Simona and Valerio to have been organized this, and I think we can conclude with an applause to everybody. And, yeah, thanks.
The summary is just thank you for being here and it went way beyond our expectations. So,
yes. We really are happy with the response that we got. There's lunch downstairs.
There's lunch downstairs. Thanks to everybody who was online, and keep in touch, and see you soon. Bye.
Bye.